Ah, le sniper. Ah oui, oui.
मोटो रेजर 50 अल्ट्रा ने फ्लिप फोन्स की दुनिया को ही फ्लिप कर दिया है।
इट इज द मोस्ट इंटेलिजेंट फ्लिप फोन। इसमें है गूगल जेमिनाई, गूगल फोटोज के एआई फीचर्स और बहुत सारी एप्स सपोर्टेड ऑन द मैसिव एक्सटर्नल डिस्प्ले।
4 इंच का कवर डिस्प्ले आता है जो सबसे बड़ा है।
इसका कैमरा अमेजिंग क्वालिटी का है। ये स्मार्टफोन बहुत ही ड्यूरेबल है। IPX8 अंडर वाटर प्रोटेक्शन गोरिल्ला ग्लास विक्टस लगा हुआ है।
प्लस इसमें है Qualcomm Snapdragon 8s Gen 3. Moto Razr 50 Ultra is truly a standout flip phone.
Motorola Razr 50 Ultra. Flip the script.
Hello, Moto.
Hello guys, so I'm quite excited to start the NLP series, that is Natural Language Processing for Machine Learning. In this video, we are going to see the entire roadmap, like how you should go ahead and prepare for natural language processing. And NLP is an amazing domain, amazing tech part with respect to machine learning or deep learning. A lot of research is basically happening in natural language processing itself. So let me go ahead and let me just share my screen and let me go ahead and let me explain about the roadmap, like how you should basically go ahead with the preparation. So to begin with, till now, probably if you know machine learning, okay, so in machine learning you have actually seen, right, we solve two different kind of problems. One is supervised, that is supervised, and the other one that we basically solve is something called as unsupervised machine learning. Now, in most of the supervised machine learning use cases where we specifically solve two different kind of problem statements like classification and regression, right? In all this problem statement, right, what we have seen is that, let's say if we have some specific set of features like F1, F2, F3, F4, like this, it can be any number of features. These features are usually called as independent features, right? So if I probably talk about this, these are my input features, or I can also say this as my independent features. Independent features, right? And similarly, I also have my output feature, which is my dependent feature, right? Which is my dependent feature. So what is our aim in a supervised machine learning model is that with respect to these features, we obviously will be having a lot of data points. In the output, it can be a classification problem or a regression problem. And over here, I may have continuous values, or I may have classified points like ones and zeros. It can be binary, it can be multi-class, okay? So let's say if I have this kind of data points over here, what is our main aim? We usually create a model, okay? We usually create a model and we train the model with this data, right? So we basically create a model and we train this particular model with this specific data set, right? With this specific data set, then our model will be able to make, or it will be capable to make some predictions whenever I give this kind of input data. Now, in machine learning, specifically, if I talk about these features, right? Now, F1 can be a continuous features, F2 can basically be a categorical features, and it can also be different types of features over here. And during this particular scenario, let's say that some of our features are completely made up of text. Let's say one basic example that I really want to give is about spam classification. Let's say this is my example over here, spam classification. Now in spam classification, what all features we may have? We may have, let's say, my main aim is to basically detect whether an email that comes to me is a spam or not spam. Okay, so let's say that this is a classification problem that I really want to solve. Now in this scenario, some of the features that I may have, one feature is that I may have something called as email subject. Okay. I may have the next feature as email body. And my output feature is basically whether this mail is spam or ham. Ham basically is not spam. So let's say over here, I'll give you one example. Let's say the email subject is like billionaire. So here you can see that it is a completely a text, right? Email body, it can be like you won a lottery of, okay, I'm just giving you an example. You won a lottery of $1 billion. And I think you get this kind of emails, right? Now, obviously, when you get this email, in real world scenario, we will be classifying these particular points, and this will basically be a spam. So I'll put a category as 1, or I can also put it as spam itself. Now, here, one thing that you can notice over here is that whenever in our input features, we have a continuous variable and we have a categorical variables, and obviously we have different techniques to convert this categorical variables into continuous values, right? There are techniques like one-hot encoding, there are techniques like target encoding, ordinal encoding, all those techniques are there, which we basically do it in feature engineering. But let's say that if my entire data is a text or a sentence like this, right? In this particular scenario, it will not be that easy for a model to understand, right? Obviously, because the model cannot understand human language, right? Right now I've written in English, tomorrow it can be in Chinese, day after tomorrow it can be in some other languages. So model is not directly capable of understanding this particular text. So what should we do in this particular scenario? So we have techniques where we can convert this all text into some meaningful vectors. Now what are vectors? Vectors are just like numbers only, but understand those vectors represent some meaningful information with respect to this particular text, okay? And whenever your input data is in form of text or sentences, we basically use something called as natural language processing, so that we'll be able to process this particular data and we'll be able to make the model understand to solve use cases like spam classification, right? So this is the entire context behind NLP, and why it is so much popular, because nowadays you see a lot of examples. Alexa, right? I think many people use Alexa, many people use Google Home, right? Many people use some automated device, like let's say the AC is running, right? And you say, hey, switch off the AC, switch on the AC. How that particular machine is able to understand that? It is all because of natural language processing. Google is extensively doing some amazing research with respect to NLP, and they're coming up with some amazing things. Yes, we will be learning both with respect to machine learning, and as we go, we'd also try to learn with respect to deep learning. But just try to understand, in this video, we are going to understand the roadmap, like how we should go ahead and prepare with respect to the NLP. So again, I'm going to write the roadmap of NLP, okay? And again, we are also going to use different libraries. I will just going to draw a pyramid kind of structure, and we will go in the bottom to top approach, okay? So let's go ahead and let's try to understand what should be the roadmap of NLP. Initially, to begin with, I'm just going to create a small block, okay? To begin with, this first block is basically, initially you need to know one programming language. So let's say that I am going to probably go ahead with Python programming language. Super important, right? With the help of Python programming language, we'll obviously be able to solve a lot of use cases of NLP. But when I go to step 1, so this is basically the step 1. The step 1 is nothing but it is basically called as text pre-processing. And this text pre-processing initially will start with some basic things. Like whenever we have this kind of text data, what are the text pre-processing things we need to do? How we can basically clean that particular text data? All those things will basically come in text pre-processing, okay? The techniques that we are probably going to apply in this is like tokenization. Tokenization is a concept wherein you convert a paragraph into a sentence into a words, different things. We're also going to learn techniques like lemmatization. We are going to learn techniques like stemming. We are also going to introduce to words like something called as stop words. All these things will basically become covering in the text pre-processing part 1. So this is basically the step 1. Okay. So I'm just going to write this as step 1. Super important, and initially we'll be starting with this. Okay, and again, the entire detailed syllabus, obviously I'm going to make video by video to make you understand each and everything, but on the 1,000 feet overview, I'm just giving you this. There are a lot of topics inside this which we really need to be familiar with. Now coming to the second one. Okay, so the second one, we basically say it as text pre-processing step 2. Okay, so again, this is also a text pre-processing technique, but we try to increase the complexity of it, and it tries to solve more problems. So here in the text pre-processing 2, here we focus on converting the text data into vectors. So here I'm just going to write it down. This is my step 2. Here I'll write, or I can basically write text pre-processing part 2. Here we are going to learn topics like bag of words, okay, TF-IDF. We're also going to learn things like unigrams, bigrams. There are a lot of concepts like this which we are going to cover it. Again, this is again a text pre-processing technique, but again, understand what is the main aim. The main aim is basically to convert, or let me just write like this, step 1 and step 2. Instead of writing like this, I will just write it in a simpler way. Okay, so here we are basically focusing on cleaning the text, right? Cleaning the input. In this particular step, we are trying to focus on converting our input text to vectors. And this is a super important step, because this vector should be able to make sure that the context of the statement should be able to get captured, right? So at the end of the day, in NLP, with whatever techniques right now it is there, like transformers, BERTs are there, which is quite advanced techniques. If you are able to convert this input text into some meaningful vectors, you will be able to solve those particular use cases in a better manner, right? So this is basically the second step where we focus on converting the input text into vectors. Still, there are more advanced techniques of text pre-processing, which I will go with the third step. And here we focus on, here I'm just going to write it as text pre-processing with respect to part 3. Okay, and here what all things we basically focus on, we use more advanced techniques, which is like word to vec, average word to vec, and this is also a technique to convert the input text into vectors. Now you may be thinking, Krish, in the second step also you have written the same thing. In the third step also you have written same thing. Yes, guys, understand, as we go from this second step to the third step, this conversion of the input text to vectors, it is better than the approach that we basically use in BOW, that is bag of words, TF-IDFs, unigram, bigrams, right? But as a learner, we really need to know all these particular steps, right? Now, over here, we focus more on techniques like word to vec and average word to vec. Here, the word to vec and average word to vec is again a kind of a deep learning technique, but we will try to learn this and we'll try to understand how it basically happens. Okay. Now, coming to the next step that we focus on, right? If we continue understanding the entire roadmap, here we also focus on understanding RNN, LSTM RNN, GRU, okay, GRU RNN. Now again, guys, this is a deep learning technique which is basically used for handling or solving text related use cases like spam classification, text summarization, and many more things. So again, over here, these are some neural networks you should be familiar with in the roadmap before basically when we enter into the deep learning part. This is super important to understand, and again, as I said, this is a part of deep learning technique. Okay, but since I'm writing about the roadmap, I really need to mention about all those things. Now coming to the next one, there is also a technique which is called as word embedding. Okay, so this is also an amazing way to convert input text into vectors. Internally, if I talk about, so this particular text pre-processing, it also uses techniques like word embedding. Okay, so this is also a technique, but this technique is basically called as word embeddings. And word embeddings internally uses some amount of word to vec, but we can train our own word embedding techniques. Okay. So again, this is a technique of converting input text into vectors. Now, similarly, we have techniques like transformers and BERTs also. So coming to the next one, this is basically transformer. Again, this is an advanced technique. I just really wanted to mention all these things to you so that you will be able to understand. But so if you really want to become a pro, you really need to go with this particular pattern and try to complete till BERT and try to see the application of that. But as we go up from bottom to top, the accuracy of the model keeps on increasing because, and remember one more thing, the size of the model also increases, right? Whichever machine learning models or deep learning models that you're probably trying to create to solve the NLP use cases, it'll keep on increasing as you go towards transformer and BERT. Now, initially, as I said, we are going to learn with respect to NLP, with respect to machine learning, NLP for machine learning. So what all things we are going to focus on? We are going to focus on these three things first. And when we'll start deep learning, we will probably focus on this three. Okay. So here, I'm just going to write this. Important thing is that all these three steps will be the part of machine learning. And now when I say machine learning, we will be using libraries like NLTK. And there are also libraries like Spacey, which will actually help us to perform all the tasks which is available over here in the bottom three. Right, but we'll focus on one library called as NLTK. So suppose if you know NLTK, I think learning Spacey is also very much easy. In the case of deep learning, we will usually go with libraries like TensorFlow or PyTorch. So both libraries are quite amazing with respect to this. As you know, TensorFlow is now an open source, PyTorch is an open source. TensorFlow has been created by Google, PyTorch has been created by Facebook, right? But at the end of the day, what is the main aim? Your input data is in the form of text data, and you basically have to perform some amazing kind of text pre-processing where you convert the input text data into vectors, and you are able to solve amazing use cases of NLP using both machine learning and deep learning. And this is a brief idea about the entire roadmap, like how we are going to prepare.
हाँ सुन रहा हूँ ओ बुआ के लिए शोपीस, लेकिन पिंकी ने तो टॉप्स मांगे थे ना. स्लो डाउन ओप्पो ये है.
Yeah,
हेल्प नाउ.
don't stress, bro.
थैंक्स ओप्पो AI.
Reno 12 series, Oppo AI phone.
I'm Brinda Bhattacharya and I'm going to be your dean for the next 2 years. Why don't we introduce ourselves?
I'm Gurpreet and I'm from Time.
I'm Sadhgi and I'm from Time.
Vishal from Time.
Nandini from Time.
Time.
Hold on. How many of you are from Time? Same story, time after time.
Hello guys, so we are going to continue the discussion with respect to NLP. And in this video, we are going to discuss about some of the amazing use cases. And these use cases, we use it every day in our day-to-day activities, right? So let me go ahead and let me share my screen and let me talk about every use cases. One by one, we'll be discussing about it. And this will give you a clear idea about what is natural language processing. Now here I've opened my Gmail tab. Now in this specific Gmail, you'll be able to see that, let's say that I really want to write some email, right? So I'll say, hello, Krish. Okay. And let's say I made a spelling mistake. Okay. I wanted to clarify. So I have actually written a wrong spelling. So here you can see that automatically the spelling has been corrected, right? And this is all because of NLP. And in this also we can, like suppose if we receive an email from someone, right? We can also write an automated email from them. So that basically means it will basically tell us that what kind of text it will auto generate and it will give it for us and we can actually send it. So I wanted to clarify about the data science. And let's say I'll write course. Okay. Now let's see what it basically gives. It can also give you a suggestion like this, and now you can basically select the course, right? So this is also one amazing use cases and we use it every day. Now let's say I go to my LinkedIn. So here Rudra Pratap Singh is one of my student, and automatically we can see that 2 tags automated replies there in the LinkedIn itself. And this is also an amazing application from NLP, so that if you really want to just provide this any of this particular 2 tag, you can just click it and you can reply back. So in short, is saving you a lot of time. Now similarly, if I go with respect to one more application, that is Google Translate, and I hope everybody uses this. Let's say that I just go ahead and write one language. I'll just say, how are you, right? And I probably want to convert this into Arabic. Okay, so it looks something like this with this specific language. Suppose if I really want to convert this into Hindi, so then you can basically say that automatically the text is coming like kya haal hai, right? In Hindi we basically say kya haal hai for how are you. So this is also happening because of NLP. Amazing application. And we use this, and in most of the websites also, right? And let's say in LinkedIn, if somebody is posting in some different language, below only you'll get an option of something called as C translation. So once you click that particular thing, and automatically it gets converted to English. Not only that, guys, let's say that I'm just going to go ahead and search for Krish Naik. So Krish Naik is my name. I'm a YouTuber. I'm also a co-founder of iNeuron.ai. But here, if I probably go and select on images, now here you can see that it is already been able to detect my image, and it is in turn converting that text into images. It is understanding the text, and it is basically thinking that okay, it knows that it is talking about myself, and based on the web, right, it is being able to capture all the images that is available in the web. So this is also an amazing thing. And probably if I go ahead and select videos, here also you'll be able to see all the videos of in my YouTube channel, or probably in all the other public platform that I have, which is being accessible via web. So this is an also amazing example, text to image, text to video, and a lot of research is also currently going on with respect to different companies. There is an amazing company which is called as Hugging Face, and Hugging Face have actually created an amazing models and solutions for solving question answering. It has basically question answering models, some summarization, text classification, translation, right? All these particular use cases are there, and you can see that how many different kind of models it has. Like for question answering, right, it has 2,380 models. Summarization, it has 588 models. For text classification, it has this much models, right? And here you can see that how many companies are basically using this. Google AI, Intel, SpeedBridge, Microsoft, Grammarly, right? All these things are basically using this. And again, this is an amazing application of NLP itself, because all these applications are, in short, taking the text data only and performing different kind of tasks on top of it. So one more amazing thing that I really want to show you as an application with respect to Alexa and Google Assistant. I have some of the Alexa Home configured over here. I can control my ACs and lights. But with respect to Google Assistant, a simple application, I can go and open it. So here I have my Google Assistant. Now here you can see that. Hey Google, do I have any doctor appointments tomorrow?
Sorry, I can't find anything on your calendar that matches that.
So now here you can see that already it is being able to retrieve from my calendar, and it is able to see whether I have a doctor appointment or not tomorrow. So this way, it is really easifying all the task with respect to most of the critical things, right, that we do in our day-to-day activities. So we use extensively NLP a lot in our day-to-day activities, and this is what we are going to learn in this specific course, how we can build this kind of models, what kind of text pre-processing actually happens. You'll get a crux idea behind it, how these applications also works. Hello guys, so we are going to continue the discussion with respect to natural language processing. In this video, we are going to cover some of the basic terminologies that is required in NLP. You really need to understand these terminologies, because I'm going to repeat these terminologies again and again when we are discussing the other topics. So the topics that is going to get covered in this video is about corpus, documents, vocabulary, words. You really need to know all these topics, what exactly it is, with some basic examples. Now, usually, whenever we get a paragraph is usually called as a corpus. Okay. With respect to documents, whenever you have any kind of sentences, you really need to understand that these sentences are also usually called as documents. What about vocabulary? Vocabulary is nothing but all the unique words that are present in this paragraph. That is basically called as vocabulary. Usually we have a dictionary, right? We usually say that what is the vocabulary in that particular dictionary. All the unique words are the count of all the unique words or all the unique words that is present in the dictionary. It is called as vocabulary. And with respect to the words, all the words that are present in a corpus, that we will basically define all those separately as a specific words itself. So these are the basic terminologies that you really need to understand. As said, in this video, we are going to discuss about something called as tokenization. And tokenization is a very important step whenever we try to solve any kind of use cases with respect to NLP. Now, what exactly is tokenization, right? So let's say that I have a paragraph. I write over here that my name is Krish. My name is Krish. Okay. And I have an interest in teaching. I have an interest in teaching machine learning, NLP, and deep learning, and DL. Now, let's say that if I have this specific text, this text I can consider basically as paragraphs. So this will be entirely corpus. Okay. So this is my entire corpus that is available, which is nothing but a paragraph of words, right? So if I probably combine all these words, it becomes a paragraph. Now, tokenization is a process wherein we take either a paragraph or a sentences and we convert this into tokens, right? Now, suppose let's say I want to perform a tokenization on this particular paragraph, and over here from this paragraph, the tokens that are usually generated, it will basically be called as sentences or documents. So let's say that I will be applying a tokenization on this, and with respect to this, let's say that I will try to convert this entire paragraph into sentence. So I may also add one more line over here. Let's say full stop. I'm just writing one more full stop over here. Okay. And I will also write that I am also a YouTuber. Okay. So these are the two sentences that is present in this paragraph. So with respect to this particular tokenization, if I perform a tokenization on this paragraph, it will basically create sentences. My first sentence in this particular case will be, my name is Krish. Okay. And I have interest in teaching ML, NLP and DL. Okay. So this is basically my document 1 or sentence 1. My next sentence that I'm going to probably write over here, because the full stop is over here, right? So when we convert from a paragraph, when we do tokenization from a paragraph into sentence, it will be looking for this kind of characters like full stop or exclamation. I'll show you practically how this can be actually done with the help of Python programming language. So the second sentence that I will probably be having is like, I am also a YouTuber, right? I am also a YouTuber. So again, if you really want to understand what exactly is tokenization, tokenization is a simple process wherein we are converting a paragraph into sentences. Now, there may also be a scenario that let's say that I have some sentences, okay? And on top of this, I can also perform tokenization again. So let's say on top of this, I'm performing a tokenization. Now this tokenization technique that I'm probably applying will convert these sentences into words, right? So let's say I say over here, it is basically getting converted into words. So each and every word will be a separate word. So my will be a separate word, name will be a separate word, is will be a separate word, Krish will be a separate word, and will be a separate word, I will be a separate word, have interest in teaching. All this will be a separate words itself, right? So this process is also called as tokenization. So in short, words can also be a token. Sentences can also be a token, right? This is very important to understand. And why it is required? Because this is a part of text pre-processing, because each and every word in NLP needs to be converted into a vectors. So we really need to take up each word and try to do this kind of pre-processing. And there are a lot of steps like cleaning and all, which I will also be showing you. But in this video, we are trying to understand about tokenization. So I hope you have got an idea about corpus, you have got an idea about sentences. Now let's go ahead and understand about vocabulary, which is also called as unique words. Okay. Now let's say I have two sentences. I like to eat apple juice. Sorry. How can we eat apple juice? I like to drink apple juice. Okay. Here I will again continue and I'll write my friend likes mango juice. Okay. Now let's say that this is my entire paragraph. Okay. Now in this paragraph, you know how many sentences are there? There are two sentences because there is a full stop over here, right? So I will just divide this into tokens. So let's say I'm going to perform something called as tokenization over here. Okay. And this will get converted into tokens. And right now the tokens that is present over here will be sentences, right? So my first sentence will be, I like to drink apple juice. So this is my first sentence. And second sentence is nothing but, because there is a full stop, my friend likes mango juice. Mango juice. Now see, when we have these sentences, obviously you can go and count each and every words, right? Let's say how many total number of words are over here. So if I probably go and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So if I again count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So total I have 11 words. But if I try to count the unique words, how many unique words are there? If I make the count again, so I will be one unique word, like another unique word, 1, 2, 3, 4, 5, 6, 7, 8, 9. See, like and likes are two different words. So I'll say 9, 10. But this juice is getting repeated. So the total number of unique words will basically be 10 words, right? Let's say instead of this likes, there was something called as like. At that point of time, the number of unique word will be 1, 2, 3, 4, 5, 6, 7, 8, 9, right? I will not count like and juice, right? But already likes is there, so it will be counted as a separate word. So whenever I get this unique word as 10 words, that basically means in my dictionary, in my this complete paragraph, this is my vocabulary. So this is all the possible words that I have, right? That is the 10 words, right? Now, since I have converted this into like, so I'm just going to make this as 9 words. I hope you are able to understand the basic differences between corpus, documents, vocabulary, and words, right? So this entire thing is super important when we are learning about tokenization. Again, if somebody asks you what is the definition of tokenization, you can just say that tokenization is a process to convert either a paragraph or a sentences into tokens. If I convert a paragraph into tokens, that basically means I'm converting a paragraph into sentences. I can also convert a paragraph into words. Hello guys, so we are going to continue the discussion with respect to NLP. In our previous video, we have already seen about tokenization. We have understood about basic terminologies like corpus, paragraph. We have understood vocabulary, we have understood about words. Now let's go ahead and do some practical things, you know, how much we'll be learning with respect to theory. So first of all, I'll just go ahead and open my Python 3 notebook file. So here, first of all, and for this, right, we are going to use libraries like NLTK. Now NLTK is one amazing library. Let me just go through this and let me just show you. NLTK is a leading platform for building Python programs to work with human language data. So if you really want to work with NLP, things like tokenization, converting a sentence into vectors can be easily done with the help of this NLTK libraries. There is also one more library which we basically say it as Spacey. So if I probably search for Spacey NLP, so here you'll be able to see that again, these all are completely open source libraries. You can also use Spacey, and I will also be showing you with the help of Spacey how you can perform different things, right? So Spacey is also there, NLTK is also there. One important assignment that I really want to give it to you is that try to find out the differences between NLTK and Spacey, and just let me know probably in the comment section of this particular video or in the upcoming videos. Okay, so this one task I want to really give it to you so that you try to understand what is the difference between these two open source libraries. Now to begin with, since we are going to initially start with NLTK, now what I'm actually going to do, I'm first of all going to install NLTK. Now here you can directly install it from here, or you can also open the command prompt and directly install NLTK, right? So what you have to do is that just write pip install NLTK. So once you do this, automatically the installation will be done. So what I'm actually going to do, I'm going to basically install from here, and I'm going to show you a tokenization example. So let me write it down, tokenization example. Okay, perfect. So this is the tokenization example. So here you can see that collecting NLTK requirement already, this is done. The installation has been done. A new release of pip is available. I don't want to update it right now because this pip will almost cover each and everything right now, right? Now this is perfect. Now what I'm actually going to do, I'm going to show you how we can perform tokenization. Like let's say if I have a paragraph, how I can convert into sentences, and then how I can convert into words. All those things I'll be discussing, and multiple ways of tokenization also I'll be showing you. Okay, so let me go ahead and let me make few cells so that I can directly go ahead and execute it. Now one thing over here, yeah, let's go ahead and let's start. Now over here, first of all, I will try to define my own corpus. Okay, corpus basically means paragraph. So let's say if I really want to create a multi-line comments, I have to basically use this triple quotes. I will write hello, welcome, comma. Okay, I'm just giving some sentences over here so that you'll be able to understand. Okay, so hello, welcome to Krish Naik's tutorials, or let's say I'll just write iNeurons, right? Or I will write something like this, Krish Naik NLP, Krish Naik's NLP's tutorials. Okay, and this is my sentence. Okay, and I can continue with my second line. So I'll write, please do watch the entire course to, I'm just writing exclamation, I'm using different characters over here, to become expert in NLP. Okay, so this is what I have actually done. I've basically defined a simple corpus which is just like a paragraph which has around 2 sentences, and I'm just going to use this particular corpus. So let's go ahead and see this corpus. Now once I see this corpus here, you can see that even though I'm just printing this, right, I can also print this. See, then that /n will go. /n indicates the new line. Okay, so if I'm probably printing corpus here, you'll be able to see the text, how it is basically visible. Now with respect to tokenization, the first step that I'm actually going to do is that I'm going to convert a sentence into paragraphs. Okay, so I'm going to basically convert a sentence into paragraphs. So for this, how do I convert it? And with the help of NLTK, it is definitely possible. So I will write from NLTK dot tokenize. Okay, and I'm going to just import. Okay, so in NLTK there is a library which is called as tokenize, and if I import the sent_tokenize. So what sent_tokenize does is that it tries to convert a paragraph into sentences. So this is the function that we are basically going to use, or functionality that is we are going to use, which is present inside NLTK.tokenize. Okay, so you can just say that this is a kind of package inside this, and I will initialize this package in order to convert a sentence into a paragraph into a sentences. So here I'm just going to write send tokenize, and let me just go ahead and give my corpus. So once I give my corpus, here you can see that it is giving us a list of sentence. So here's, you can see over here, this is my sentence over here, hello, welcome to Krish Naik's NLP tutorial. So here you can see this is my first sentence and this is my second sentence. And from exclamation also it has divided it because I'm getting 3, right? So here you can see hello, welcome to Krish Naik's NLP tutorials, full stop. As soon as it finds full stop, it is just going to make a next sentence. So here wherever /n was present, it is using that. And wherever exclamation is also present, it is basically making sure that a new sentence is getting created with respect to that. And that is what send tokenize actually does. If you really want to find out the definition of this, here you can see that you can also provide different languages. What are languages it supports? You can just go ahead and have a look onto that. And if you don't find much documentation out of it, so what you can do over here, you can just go and search for NLTK send tokenize, right? Send tokenize. So you will be able to find out the documentation page directly, and you can refer it from here, right? There are different tokenization. See, send tokenize is there, word tokenize is there, which we are basically going to discuss. Right now, we are going to focus on this, okay? So in short, it returns a sent tokenized copy of text using NLTK's recommended sentence tokenizer. And current class, it uses this called as punct send tokenizer. So along with the full stop, it is making sure that wherever exclamation is basically coming, it is going to make as another sentence. So this is perfect. We are able to get this right now. I will go with the next tokenization. And before that, what I also want is that if I probably save this in a list of sentences, so let's say this sentence is also called as documents, which I have already discussed in my previous class, previous session, right? So if I probably go and see these documents, this is basically my list. You can also check out with the help of type. So type documents, right? And if I probably want to iterate through this, let's say from sent in documents, for sentences, for sentence in documents, I can also print this sentence parallelly, right? So here I can just define it as sentence. So this is my first sentence, second sentence, and third sentence. This is perfect. We were able to do with respect to the sentences. Now let's go ahead and do it with respect to the word tokenize. So next tokenization technique, what I am actually going to do is that next tokenization is that I can convert a paragraph. I can convert a paragraph into words. I can also convert a sentence into words. Sentence into words. Okay. Perfect. Now for this, what I'm actually going to do, first of all, let's go ahead and see with respect to paragraph. So already you know that with respect to converting a paragraph into words, I'll be using again another library. So I can write from NLTK dot, okay, tokenize. From NLTK dot tokenize. Okay, spelling mistake is there. So tokenize, I'm going to import word. Let me just write it down, word tokenize. Okay, so here we can basically use this word tokenize over here, and let me just execute it over here, and let me go ahead and write word tokenize. And here, if I directly give out my corpus, here you can see that each and every word has been divided. Hello world and hello welcome. Here you can see all the characters like comma, full stop has been treated as a separate character altogether or separate words altogether, right? So here you can definitely clearly see that each and every word has been splitted with respect to this. Only one word that is not having this, right? So if I probably go and see over here, hello, welcome to Krish Naik's. So this kind of word has not been splitted. This all is being considered as a single word. But if I consider with respect to full stop, with respect to exclamation, with respect to comma, it has been considered as a separate word. So here also you can find it out with respect to this, right? So this is very simple with respect to converting a paragraph into words. And why do we do this? Because each and every word will have a different importance, and we really need to perform some pre-processing on top of it. So right now, initially when you get it, you know, which are the important words, you have to take it, you have to pre-process, you have to clean it, you know, and that is the reason why we specifically focus on each and every word. Okay, so this was about the word tokenize. And now with respect to sentences also, you know that how you can basically do, just go over here and just paste it over here for sentences in this. Now here you're printing the sentences, right? Now what you can basically do in that is that after you probably get this sentence, after you get this sentence all together, you can just directly apply word tokenize, right? So here you can basically write word tokenize on sentences. So you will be able to print everything over here. right? So hello, welcome to this. Please do watch the entire course. This is there, right? Perfect. So here we have seen that how we can basically convert a sentence into words, right? Now you can also do one thing over here is that you can use one more library. Let me just talk about one more library. Probably you have seen that. So I'm going to just write word punct tokenize, and in this word punct tokenize, what we are basically going to do is that if I try to apply this, if I try to initialize this word punct tokenize, and if I try to provide my corpus, let's say, so here you just try to find out the difference. And one difference that is clearly seen is that this apostrophe S has also got splitted. Before it was not getting splitted, right? See, apostrophe S was a single word, but now you can see that it has been splitted. So that is the reason why we are using this punctuations. This punctuation is basically making sure that the punctuation will also be treated as a separate word. Perfect. So this is good. There is also one more technique which is basically called as a tree bank word tokenizer. And also again, I'll try to tell you the difference, what exactly it is with respect to tree bank word tokenizer. So I'll just try to execute it and you try to find out the differences with respect to that. Let's see how much you'll be able to do. So I will write from nltk dot tokenize import tree bank tokenizer. So I will initialize this tree bank tokenizer. Okay, let's say that I'm initializing this into tokenizer, something like this, something to one variable. And then I can basically use a function which is called as tokenizer dot tokenize. And once I give my corpus, here you'll be able to see that I'm actually able to get it. Okay, now just see over this, what is the difference with respect to this. You will definitely be able to find out some difference when comparing with this specific thing. Okay, so just let me know what is the difference that you are able to see. I know there is a very minute difference. So with let me tell you the answer. You can just pause for some time but you can check it out. But let me tell you an answer. With the help of tree bank word tokenizer, here you can see that full stop will not be treated as a separate word. It will be included in the previous word itself. Now here you can see that full stop was a separate word. Here also you can see that full stop is a separate word, right? But with respect to the last word, right, full stop will be separate, you know, because here you can see that, right? If I probably see the sentence, right? After this, we have a new line, right? And after this, our sentence is getting closed. For the last full stop only, it will be considering as a separate word. But with respect to this particular full stop, it will be considering as a part of this. It will not be considered as a separate word. Only this is the difference with respect to this. And again, it can be handy in some of the use cases, but not in all. But in a generic way, we basically most of the time use word tokenize or send tokenize, right? So yes, this was it with respect to the tokenization example. I hope you like this particular video. Hello guys. So we are going to continue the discussion with respect to natural language processing. And now we are going to move towards some more techniques with respect to text pre-processing. Already in our previous video, we have seen tokenization. We have seen that how we can convert a paragraph into sentences and then probably a paragraph into words, or converting a sentences into words, right? So in short, we have seen that how we can actually do tokenization with the help of NLTK. So in this video, we are going to focus on something called as stemming, which is a very important process altogether. And what exactly is stemming? I'll also provide you the definition. We'll also see a lot of examples with respect to that. And we'll also try to see the different types of stemming. So I have opened a file over here. So here you can see regarding this stemming, and I have also given the definition. Now let's understand what exactly this is with some good examples. Now, first of all, we'll see the definition. Over here, it shows that stemming, and this definition is taken from the Wikipedia. So stemming is the process of reducing a word to its word stem. Okay, this is super important, guys. To its word stem that affixes or suffixes or prefixes or to the roots of the word known as lemma. Okay, stemming is important in natural language understanding and natural language processing. Now, what exactly this is? I'll tell you some examples. Let's say I want to just create some cell below. Okay, over here, if I have a lot of text, right? Let's say that I'm trying to solve a sentiment, or I'm just trying to solve a classification problem. And the classification problem is very simple. We basically need to find out whether the comments on the product is a positive review or negative review, right? So when we are solving this kind of problem statement, so in this, what we'll be having in our data set, we'll be having the comments or reviews, I can say. I'll be having reviews, and based on this particular reviews, and this reviews will obviously be some kind of text data, and we need to basically create a model where then we can basically classify whether it is a positive review or negative review. That is very simple. Now, usually in this reviews, let's say that I have some of the words like eating, okay, or it can be eat, right, or it can be like eaten, right? It can be different kind of words, but at the end of the day, it actually represents the same thing regarding eating, right? So this is basically eat. Eat is the root word, or I can also say it is the stem word stem of this all the words, right? Because eat is very much common. And having this variety of words for a problem statement will not impact much with respect to finding the output like positive or negative review. Try to understand what I'm actually trying to say. Over here, I may have different kind of words like eating, eat, eaten, or there may be also other words like I can also make a combination of like going, gone, right? Gone, goes, right? At the end of the day, it is basically talking about go, right? So go is a word stem of all these words that are present, right? So it is not necessary that we need to have similar kind of words again and again, because this increases the number of input features in short, because each and every word represents a vector, as we'll see as we'll go ahead. After text pre-processing, we'll try to convert this text into vectors. So having this similar kind of words, instead of having this similar kind of words, I can just have one word that is just like go, right? And we'll try to solve the problem with respect to that. So stemming is actually helping us to do the same thing. So finding this word stem can be actually done with the help of stemming. And there is also a concept which is called as lemmatization. We'll try to understand the difference as we go ahead. But first of all, let's go ahead and see that how with the help of NLTK we can perform stemming. Okay. So what I'm actually going to do is that I'm just going to take some examples. Let's say that I have all these words. Okay. So I'm just going to remove this. And let's say that I have all these words. Now, right now you have words like eating, eats, eaten, writing, writes, programming, programs, history, finally, and finalized. Okay, so I'm just going to execute it, and let me make some more cells. Okay, so I'm just going to delete this cell because I don't require it. Okay, I'll just create a cell below. Okay, and let me press escape and let us go ahead, right? So here you can see all these particular words are there. Now let's see how we can find out the word stem of all these particular words with the help of stemming. The first stemming technique that we are probably going to use is something called as Porter stemmer. Okay, Porter stemmer. And there are again different types of stemming techniques, which I will probably be showing you. And then we'll be able to understand that what all things it will be able to give us. Okay. Now, in order to apply this Porter stemmer, it is very much simple. In NLTK, already those functionalities basically present. So I will just write from NLTK dot stem import Porter stemmer. Okay. So once I initialize this, here you can see this, I'm going to use this Porter stemmer, which is just a kind of class. And for this, we have to initialize it. We have to initialize an object for that. So let me just create an object, and this will basically be my stemming. And once I do this, now in the next step, what I'm actually going to do for each and every word, I'm just going to apply this stemming process. Okay. So it's very simple. How do I do it? I will just iterate it. So I'll say for word in words, right? And here I'm just basically going to write print, and let me write it down as word plus, I'll just give some type of marking. This is the word, and the stemmed part will be nothing but I'll be using the same object stemming dot stem. There is a functionality, there is a function called as stem, which will actually, whenever we push any words inside this, it will do the stemming thing. That basically means for eating, probably it may give you eat. For eats, it may give you eat, right? So something like that. So I'm just going to give my word over here. So once I execute, now here you can see that perfect. Eating is coming as eat, eats comes as eat, Eaten is coming as eaten only. Writing is coming as write, which is good. Writes comes as write. Programming comes with program. Programs is nothing but program. History. Here you can see history is becoming HISTORI. So here it is a major issue, right? And I'll also talk about the disadvantages. Finally becomes final. Finalized becomes final. This is there, right? Now let's say that over here it looks good, right? Probably for eaten, you can see that nothing has happened. It is given the same word. But if you see some words like history, now here you are actually getting history, RI. So the entire meaning of this particular word has actually changed. And this is the major disadvantage of stemming. When stemming is basically applied, for some of the words, you may not get a correct exact meaning. The form of that specific word may change. So this is the major disadvantage with respect to stemming. Let me show you some more examples. Now suppose if I say stemming dot stem, I'm just going to apply this particular stem word on a word called as congratulations. Okay. And if I execute it, here you can see the meaning of the word is basically changing. It should have told like something like congratulate, right? But here you can see congratulate. It is basically changing the form of the word. Now the word does not have any kind of meaning, right? So this is again one major disadvantage of stemming. Okay. Similarly, if I probably try to show you something like stemming.stem, and if I probably write something like sitting, so here you will be able to see, let me just write it down, sit. Now see, for sitting, it is giving a very good word. So that basically means stemming works for very good number of words, but for some words, it does not give you us a good answer, right? So this is the major disadvantage of stemming, and this all will get fixed with the help of lemmatization. But whenever you have any kind of problem statements like classification problem, review classification, or we really want to see whether an email is a spam or a ham, right? Whether it is a spam or not a spam, we should definitely go ahead with using stemming, and again, some of the words will not come in the right form, but yes, instead of using Porter stemmer, we have other different kind of stemmer techniques which we can definitely use to improve it. Okay. Now let me go with respect to the second one. Now with respect to the second one, I'm just going to delete this cell because we don't require it. The second cell is that which is called as the reges stemmer class. Now this regular expression stemmer class, it is nothing but this is a class with the help of which we can easily implement regular expression stemmer algorithm. So we can just provide a regular expression and it will be able to apply the stemming purpose in that. Okay. So it basically takes a single regular expression and remove any prefix or suffix that matches the expression. Perfect. Now what I'll do, I'll just create a cell below, and again, I will make some more cells and I'll try to show you some example. Now, first of all, we need to initialize this. So I will write from nltk.stem import, what is the name? Regex, right? So I'm just going to write regex stem. Perfect. Then we basically need to initialize it. So I'll say reg_stemmer is equal to regex stemmer, right? So I've initialized it. This is perfect. It is giving us an error saying that regular expression is required. Now this is super important. Now let's go ahead and press shift and tab. Now here you can see the first parameter that goes is something called as regular expression. Okay, and this is some minimum value. We'll try to understand what exactly it is. Now here you can see a stemmer that uses regular expression to identify morphology affixes, right? Understand this, morphological affixes. I'll try to show you an example. If you don't know the meaning of this, any substring that match the regular expression will be removed. So this morphological affixes is basically, in short, a regular expression which will match whatever words we are basically giving, and if it matches, it will get removed. Okay. Now let's take some example. Okay, over here, and here you can see that this param is the minimum length of the string to stem. Okay, so if the minimum length is somewhere around 4, then only you will be able to apply this. So I'm just going to apply this same thing, and I'm going to paste it over here. Okay, so here is my reg stemmer. Now what I'm actually going to do, I'm just going to write reg.stemmer. Now you should understand over here what I have actually given. I have given ing dollar. Okay, here I am given s dollar, e dollar, able dollar. Okay, so I've given all this regular expression, and this will make completely sense when I will be implementing it. Now you see, just pause the video and just let me know what is the output that you feel will be getting for this. Eating. Now eating, you should see over here, ing is there, a regular expression is there. So, but dollar is also there. Okay, this is super important. Dollar is also there. Now, if I try to execute this, I'm able to get something called as eat. Okay. Now, in short, what this is happening is that this is basically saying that wherever on the last word it is ing or it is s or it is e or it is able, just try to remove that. Now, the next example that I really want to give is that, let's say I have this particular word, ing. Okay, so here you can see ing eating, right? What do you think the output will be? Whether it will be eat or whether it will be something else? Okay, so here if I try to execute it, here you'll be seeing ing eat. Why? Because the regular expression says that only in the last with dollar. If I probably remove dollar and if I just execute it, now see, everything will get removed. Okay, or probably I just want in the starting, so I'll just use this. So here you can see ing eating. So this will not work. Okay, so we can basically have something like this, and we can basically check how we can actually remove it. So this is perfect. So here you can see wherever ing is there, it is getting removed. Perfect. So this is good. We have done this. Okay, ing eat. Now let's say that I also want to try something else. You can definitely try with different word. You can use this able, e, s, whatever regular expression you can basically write. You can go ahead and write it and you can check it. Okay, so this is with respect to regular expression stemmer class. Now the next one that we are basically going to discuss, and let's see where this is. Porter stemmer, this. Again, it has written the same thing. I don't want to write the same thing. I'll go ahead with something called as snowball stemmer. And this is also an amazing technique. And this is a better technique when compared to, okay. So snowball stemmer, I think I've given the definition somewhere here. No. Okay. Snowball stemmer is again a stemming technique, but in this snowball stemmer, it performs better than this Porter stemmer. Okay, that is the reason why snowball stemmer had actually come. Initially, we came up with Porter stemmer. We saw that a lot of words were getting messed up, you know. So that is the reason why we use snowball stemmer, because it gives a better accuracy when compared to the Porter stemmer. When I say accuracy, better form of a word. Okay. Now for using snowball stemmer, what I'll do, I'll write from sklearn.stem import snowball stemmer. So here you can see, I'll just write snowball. For my sklearn, oh, not for my sklearn, sorry, from NLTK, because it is basically present in the NLTK, right? So from NLTK.stem import snowball stemmer, and I'm just going to import it. Then we are going to initialize with respect to snowball stemmer, and let's see what are the parameters. So here, first of all, snowball stemmer is also provided with different languages like Arabic, okay, Danish, English, Finnish, French, German, Hungarian, Italian. So you can use basically all these words. Okay. So for right now, I'm just going to use English. So what I'm going to do is that I'm in quotes. I will just say English. Okay. And I'll just use this. And finally, I will basically use a snowball stemmer over here. I will just create a variable. Okay. And just execute it. Perfect. Now, the next thing is that I will just use another condition saying that for word in words. Okay. And I'll just write for words in words. So I'll write snowball stemmer dot stem on word. Okay. But I'll print this in a better way so that you'll be able to understand it. So print word plus, and this will be like this, something like this. Just for formatting purpose, I'm writing this so that it'll look good better for you all. And here I'm just going to write the word, right? So same thing what I did in the things. So here you can see that I'm getting eating as eat, eats as eat, eaten as eat, right. This is all fine, right? For history also, it is not being able to give the correct form, right? Then you may be thinking, Krish, then what is the difference, right? But let's see with respect to some Porter stemmer, where this Porter stemmer will give some bad results or bad form of the word, and where the snowball will give us a better form of a word. So for this, I'm just going to execute this line of code. So here you can see when I'm applying this stemming was for the Porter stemmer, right? When I apply stemming.stem on fairly and sportingly, So what is the output that I'm getting? I'm getting fairly and sportingly, right? Li. But if I try to use the same word with respect to snowball, right? Here you'll be able to see, just let me write the snowball stemmer. Here you will be able to see I am getting some amazing answers. Snowball stemmer, okay. Okay, let me just remove this. I think there is a problem with respect to this. Now it will work, okay. Snowball stemmer, comma. I will just copy this and I'll apply to the same word something called as sportingly, okay. So now if you probably go and see, I'm getting a good output, which is like fair and sport. So altogether, you will be seeing that snowball stemmer, when applied to various other words, performs better than stemming, right? So here, see, Porter stemmer is obviously a technique where you'll be able to find out the word stem, but for many of the words, it is not being able to give a good answers. Some of the examples are like fairly, sportingly and all. Now, in order to overcome this disadvantage, snowball stemmer is basically used. And again, guys, understand these are some techniques which will actually help you to find out the word stem. And where it is specifically getting used in text pre-processing, you really need to clean the data. You need to make sure that the data is ready so that we will be able to convert it into vectors in an efficient way, right? So in this part, we have seen about stemming. And again, one major disadvantage of stemming is that obviously, see, even though snowball stemmer is performing exceptionally well, but some of the words like history, there'll be also something like going, right? So suppose if I probably write this, right, snowball dot stem, right? And if I use going, I think going, whether it will give us good or not. So going is performing well. If I write goes, so here you can see for goes also it gives us a bad word, right? Even stemming.stem, if I probably try to see this, right? So in short, how much we try, right? For some of the words, obviously the form of the word is changing. So this is one of the disadvantages with respect to stemming. And understand that for use cases like chatbots and all, these techniques cannot be used. So for that, we have to go ahead with something called as lemmatization, because lemmatization solves all this particular problem because it has the dictionary of all the words, all the root words that is basically there. So whatever word you basically give, it will be giving you a good grammatical form of the word. Like if I'm giving goes, it will be go. If I'm giving fairly, it will be fair. You know, if I'm giving eating, it will be eat. So that kind of disadvantage is getting removed completely with the help of lemmatization. And that particular part we'll be seeing in the next video. So I hope you have understood till here. Please make sure that you try, practice with different examples. Hello guys, so we are going to continue the discussion with respect to natural language processing. In this video, we are going to discuss about lemmatization. In our previous video, we have already seen something called as stemming. We understood that stemming is the process of reducing a word to its word stem, right? And we understood what is the disadvantage of stemming, because for some of the words, right, when we perform stemming, we do not get the correct form of the word, and the entire meaning of the word actually gets changed. And please remember this word which is called as word stem, right? So in short, this is just a kind of algorithm which tries to find out the word stem. But for some of the words, it is working absolutely fine. We have seen different types of stemming techniques like Porter stemmer, Regis stemmer, snowball stemmer, and we also found out that snowball stemmer was better than Porter stemmer. So all these things were covered. Today in this video, right now in this video, we're going to discuss about lemmatization, and the lemmatization technique that we are going to use is something called as word net lemmatizer. I've already told you what is the disadvantage of stemming, because the words that we are getting is not in the correct form. The meaning of the word is basically changing. So in order to prevent that, we use something called as lemmatizer. And in this, we have something called as word net lemmatizer. Now, what is lemmatizer? Okay. Lemmatization technique is like stemming. The output we will get after lemmatization is called lemma, which is a root word. Understand this, which is a root word. Like suppose if I have eating, then it will become eat is the root word, right? If I probably talk about history, history is the root word, right? If I talk about goes, go is the root word, right? Over here, we are getting the stem word, right? In stemming. right? It will probably apply an algorithm, and with respect to that, it will try to find out the stem word, right? Word stem, we basically say it this as. But here we get the root exact word. So again, the main aim of Lematizer is to give you the exact form of the word, which is meaningful, and it does not change the meaning as it was happening in stemming itself. So here you have, rather than the root stem, the output of the stemming. Now again, I'll repeat the definition. Lemmatization technique is like a stemming. The output we will get after lemmatization is called lemma, which is a root word rather than the root stem, the output of stemming. After lemmatization, we'll be getting a valid word that means the same thing. So suppose if there are words like eating, eats, eaten, it will become eat only, right? So it will be giving you a meaningful word which will represent many words over there. Okay, so NLTK provides wordlet lematizer class, and I'll try to show you with respect to this. And understand, guys, this lemmatization occurs, or it gets performed with the help of this wordnet corpus reader. So there will be a dictionary kind of words which will be comparing from there, and will be able to do the wordlet lematizer very much properly. So first of all, let's go ahead and see that how we can basically implement it. So first of all, I will try to import from an NLTK stem, import wordnet lematizer. Okay, so I'm just going to import this, and this wordnet lematizer again helps us to perform lemmatization. So first of all, I'll create an object. So I will write lematizer, and here I'm just going to write wordlet lematizer. So here, if I see this, it is nothing but wordlet lematizer. So let me just go ahead and execute it. So this has got executed perfectly. Now, one thing that you really need to see that, okay, so I will just be writing something called as, let's try some easy word. Okay, so lematizer is equal to, I'm just going to say dot lemmatize. So there is a function which is called as lemmatize, and here I have to give my words. So let's say if I'm giving going, and if I try to see the answer, I'm actually getting going. So that basically means that it is trying to find out the root word with respect to this. But let's go ahead and see the functionality of lemmatize. In lemmatize, we give two important parameters. One is word, and this is something called as post tag. Okay, I will talk about this post tag. Right now it is written as n. N basically means this word that I'm actually passing, it is being treated as a noun. So you may be thinking, Krish, how many post tags will be there? So let me just write down a comment over here. Okay, so here you have different post tag. For noun, we give it as small n. For verb, we give it as v. For adjective, we give it as a. For adverb, we give it as r. Now what I'm actually going to do, by default right now, the post tag is n, right? So with respect to n, I'm getting this output. Okay, let's say I change it to v, because I just want to show you whether this will be changed or not. Now when I give post tag as n, I'm just saying that consider going as a noun keyword, but going is not a noun keyword, right? But if I consider with respect to verb, now you see with respect to verb, I'm able to get a good lemmatization, that is like go. Okay, similarly, if I probably try to see with respect to a adjective, so here you can see I'm getting going, right? And obviously this going is a kind of verb, right? It is not an adjective. And let's say if I try to go with respect to adverb, here also I'm getting going, right? Now with respect to this going word, right, I feel verb is the correct one which we really need to select it. Now let me do one thing. All the words that I had copied over here, right? Let's apply this entire lemmatization on this entire words. Okay, so I'm just going to execute this and execute it, and again I'm just going to write this for loop. Okay, and I'm just going to copy this. Instead of writing stemming.stem, I'm just going to write lemmatizer dot lemmatize. Okay, and I'm just going to apply for these words. Now see this, eating is becoming eating, eats becomes eat, eaten, writing, writes, programming, programs has become program, because again by default in this lemmatize, remember that I've given my post tag as n, right? We are considering that all these words are basically noun. Okay, so programming, programs, history, finally, so here you'll be seeing that lemmatization has not occurred that much. We have not done any kind of, we are not able to find out, because it is being considered as noun. And in noun, whenever we give noun, suppose let's say that all my words has names, and in names, obviously those lemmatization does not occur, right? So if I have like Krishna, if I have Sudhanshu Kumar, if I have this kind of words, which is name, right? In short, this is nouns, right? We have some famous place name like Taj Mahal, India, places name and all, right? So this all will be considered as nouns, right? So that basic difference you really need to know in order to understand this. Let's say that I want to again convert this into adjective. So here you can see eating has become eats, writing, everything is same, right? But now let me try with respect to verb, because most of these words are basically verbs itself, right? So here you can see eating has become eat, eats has become eat, writing write, programming program, this history. Now you can see this, right? History is becoming as history only. In stemming, we used to get something like history, right? So this is quite amazing, right? Finally, and this all. And we could also see that in stemming, right? We also have some of the words which was not actually being able to perform well, right? Like fairly and sportingly and all, right? And even goes, right? So suppose if I probably go ahead and write something like lematizer dot lematize, and let's say I'm going to write something like goes, right? So I'm going to get go, which is good, right? And here I can also play with post tag, right? So let's say if I'm using a v post tag, I'm going to get go. Let me go and try with this. So here I'm just going to write lematizer, okay? And I'm just going to say try to do with this fairly. Let's see what kind of output we are getting. Now this lematizer is super amazing, right? Because it is giving you the good word form and the meaning of the word is also maintained, right? So here you can see fairly, sportingly. Now let me write a post tag, obviously because it was noun, so it may not give you something. So here also with respect to verb also I'm getting the same answer, which is good, right? So this is just to tell you that how good lemmatization is. But one question that I really wanted to ask you, which will take more time, word-length lemmatizer or stemming? The answer is simple, word-length lemmatizer. Why? Because you can see NLTK provides word-length lemmatizer class within a thin wrapper around a word-net corpus. So it is going to compare from there, right? It uses morphe function to the word-net corpus reader class to find a lemma. So this will basically take time. Right now I just have some number of words, so it is happening very fast. But if you have a paragraph, if you have a bigger sentence, lemmatization is going to take time, right? So this is the basic difference between stemming and lemmatization. For which use cases you can use this? One simple use case is if I really want to write Q&A, chatbots, right? Chatbots. All this is an amazing examples for all this, right? You can basically use this, right? So let me write it down. Q&A, chatbots, right? Text summarization, right? Q&A, these are some of the examples which you can basically consider. Text summarization is also one example, and in many companies it is being used. So right, so you can use basically all these things and you can basically implement a word-length lemmatizers over there, because you get the exact good form of the word, that is the root form of the word, which is meaningful, right? Hello guys, so we'll be continuing the discussion with respect to natural language processing. We are still in text pre-processing techniques. We have seen tokenization, we have seen stemming, we have also seen its different types. Along with that, we have seen lemmatization. Now we are going to consider a topic which is called as stop words. So in this video, I'm going to discuss about stop words, the importance of stop words. And again, I'll show you with the help of NLTK. Now, text processing is a very important step in natural language processing, because you really need to clean the data, you need to make the data in the right format. Later on, we'll try to convert all this text data into vectors, and then only we'll be able to train the model. Because model, you know, whenever we say any machine learning model, internally, we really need to train with some mathematical equations. So whenever we train something with mathematical equations, there we really need to give the input data in the form of numerical or floating values. So let us go ahead and let's just understand what exactly stop words is. So I've opened a new notebook file over here. So here I have one amazing speech from Dr. APJ Abdul Kalam. He was the former president of India, and it was an amazing speech. You can probably read out completely over here, and obviously it is given in the materials. Now what I'm actually going to do is that I'm going to probably talk about stop words and why it is important that we should try to remove the stop words, okay? And just for a definition, what exactly is stop words? Now here in this particular speech, you can see that there are a lot of sentences like, I have 3 visions for India. In 3,000 years of our history, people from all over the world have come and invaded us. So this is the entire speech. It is an amazing speech. If you're probably learning it, I would like to just tell you that please read this. You'll be getting a lot of information out of it. Very motivational speech altogether. Now, from this particular speech, you can see that, and I can definitely say this as paragraph or corpus, right? Now, here, there are some words like I, the, have, and, let's say off, the, to, there, why, right? All this kind of words, right? It will not play a very big role when we are doing task like spam classification, or let's say if you are trying to do some kind of task with respect to, like spam or ham classification. I have already told about that. And along with that, to just see that whether this is a positive review or negative review. But some of the words like not can actually play a very important role, not and all. So what we do is that with the help of stop words, we try to remove this particular words, because with this kind of use cases where you're specifically focusing on some of the important words to determine the output, these all words like I, the, he, she, of, there is not at all required. So what we can do is that we can basically pass this entire paragraph to that particular stop words and see that what all words can be basically removed. Okay. And that is the importance of stop words in short. So let us go ahead. Right now, I'll just go ahead and execute it. Let me make some cells so that it'll be very much easy for you all to understand. And how we can apply stop words. Along with stop words, you can also apply stemming. So I'll show you both the combination, which will be super important for everyone. Okay, so let's go ahead and let's try to do that. Okay, now first of all, I really need to import for stemming. You obviously know what we need to import. So for stemming, I'll write for nltk.stem import porter stemmer. So I can basically write porter stemmer over here and I'll execute it. Along with this, I obviously need to also import stop words, because stop words for English, it will be different, because you'll be having that entire list of words like the, he, she and all, right? So what I'm going to do is that I'm going to say that from nltk dot corpus import stop words. So from this, I will be able to use the stop words itself. So now I have imported from nltk.corpus import stop words. Now this stop words, I have to also download it. So for that, let me do one thing. I'll also import nltk and I will execute it. And along with that, I'll write nltk.download. And here in this parameter, I am going to give about the stop words. And there are different language stop words also, and we'll also try to see that. So if I probably write this, here you'll be able to see that downloading package stop words to this particular location. So the package stop words is already up to date and I'm getting true. So in short, I've downloaded all the different languages stop words, which is already present in the NLTK library. Perfect. Now we have done that. Now let's see that what are the stop words that are available in English. So in order to do that, I have already imported from nltk.corpus import stop words. I'll take this stop words, I'll copy and paste it over here. And I will say dot download. Okay. Or instead of download, I will just write dot words. And here I just need to give my language, like what language I really want to give it for, like English or something else like German and all. So I'm just going to write this. Let me just write English. And if I execute this here, now you can see the list of all the stop words that you obviously have, and all the stop words can actually be removed, right? Now you may be thinking, Krish, this may depend on data to data, right? Now here you can see that, guys, this is a list. You can also create your own stop words in English. Like let's say over here, some of the important words are like aren't, couldn't, right? These all words can actually play a very important role to find out whether a statement is positive or negative. Like not is also there. If you probably search for it, not, you will also be able to find it not. Okay. So it is always a good way that you create your own stop words and try to remove all those kind of words from the paragraph. So I hope everybody is able to understand. Now with respect to English, you have this. Now let's see whether we have with respect to different languages. And obviously you can go ahead and check the documentation, but I will just try to show you with respect to German. So in German also you have this specific stop words. Along with this, you can also use French. You have this particular stop words. So with respect to different text or different language of text, you can definitely apply different stop words with respect to that. Now you may be thinking, is there Hindi or Arabic or some other? I think for Arabic also, I think it is there. Let's see whether it is there or not. Yes, for Arabic also it is there, but I did not find it for Hindi, I guess. So again, from the documentation, you can check it out, but till Arabic, I was able to see it. Again, all the information will be given in the NLTK documentation. Now, what I'm actually going to do is that my sentence is already English, right? Now I'm going to perform two important tasks. One is I will apply stemming, and before applying stemming, what I'm actually going to do, wherever I find out the stop words, I'm just going to remove the stop words from this particular paragraph so that this entire paragraph will be shortened up, right? So for that, what I'm actually going to do, now see, whatever things you have learned from starting, everything I'm actually going to cover up, okay? So first thing first, I'm just going to say from NLTK dot stem, I'm going to import porter stemmer, and I'll go to just execute. I'm just going to execute this, okay? And then what I'm actually going to do is that I'm just going to write stemmer is equal to porter stemmer. This we really need to initialize it. Now, when we do this task, right? Now, the next step, what I'm actually going to do is that I'm going to perform the tokenization on the entire paragraph. So for that, I can use NLTK dot sent tokenize. And here I'm just going to give my paragraph. Now see this, guys. Here I'm going to get my entire sentences. Like, see, I have 3 visions for India. That in 3,000 years, this all things I'm able to get. And this is my second sentence, third sentence, fourth sentence. Like this, all the sentences in the form of list I'm able to get just by using sent_tokenize, right? This is a tokenization process wherein we take a paragraph, divide that into sentences. Okay. Now let me do one thing is that I'm just going to save this in a variable which is called as sentences, which will later become a list, right? So this is my sentences, and if you probably see the type of sentences, I'm just going to basically see this. It is a list. Now, perfect. Till here, we have done it amazingly well, right? We have done porter stemmer on that. We have initialized stemmer over here, and we have tokenized it. Now understand. What we are going to do is that I'm going to traverse through all the sentences. First of all, apply a stop words, which all words are not present in the stop words. We are only going to take that and apply stemming. This is what we really want to do. So here I'm just saying that, first of all, apply stop words and filter, and then apply tokenization, right? Then apply stemming. So this is the step that I'm actually going to do. Now see this, very simple, very important. So I'll write a for loop saying that for I in range, and here I'm going to basically give the length of the sentences. I can also go with respect to sentences, but there I'll not be getting the indexes. Here I'll be getting the indexes, okay? So range basically says that whatever length I'm actually giving, that becomes an index, right? 0 to that specific length. Now, what I'm actually going to take, I'm going to take this specific I, and I'm going to write NLTK dot word tokenize, because I'm getting in the form of sentences. I need to get each and every word, right? So I'm getting the word over here, and inside word underscore tokenize, I'll give sentence of I, because this will be an index. Sentences of I. So this will be an index, and here I'll be able to get the word. So here, what I'll do, I'll make a list of words. So in short, I'll be getting the list of words inside the sentences. Perfect. Now till here we have done it. Now after this, we are going to apply one very important thing. That is, first of all, I need to apply stop words for each and every word and see whether it falls in the stop word or not. If it does not fall in the stop word, then only I have to do the stemming. So understand the task step by step. This is super important with respect to all the steps that I'm actually taking up. Okay. So here I will write a list comprehension. I will say stemmer.stem. Okay. And here I'm going to write dot word, okay, of the word, because from this particular words, this words is a list of words. Now I have to take each and every word. So here I will write a for loop, okay, and this is called as list comprehension. So I'll write for word in words if word not in. See, if the word is not present in the stop words, then only you apply stemming. That is what I'm actually trying to do. Okay, so here you can basically see if the word is not in, I'll use a set. Along with that, I will download all the stop words with respect to English, right? So why I'm using set? Because some of the words may get repeated, so I don't want that. So I'm going to basically write it over here, right? Now through this, what I'm actually going to do, I'll get that specific word that is not present in the stop words, and only stemming will be getting applied to that specific word. Perfect. Now here, what I'm actually going to do is that I'm going to save it in a variable called as words. Perfect. I hope it is very much clear. I'm getting back everything after doing the stemming back in the words itself. And then finally, what I'm actually going to do is that I'm going to take this sentences and I'm going to replace it on the same index with respect to this words. But once we get this words, right, I need to join all these words together. So how do I join? There will obviously be a space dot, I'll just use dot join so that it will join together and it will convert that into a sentences. So this exactly is converting all the words into sentences, right? This is very much simple and we have actually done this. Perfect. So here, what all things we have done, again, let me repeat, I'm iterating through each and every sentence, and then I'm doing a word tokenize. That basically means for every sentence I'm getting the list of words, and from that list of words I'm iterating. I'm seeing that whether it is present in the stop words. If it is not present, I'm doing the stemming. After stemming, I'm again storing it back in that same list, and then I'm converting all these words into sentences. I can say converting all the list of words into sentences. Perfect. Now once I execute it, and now if I go and see my sentences, here you'll be able to see now I3 Vision India, right? In 3000 year history, right? So here HISTORY became RI, okay? People, it became people. World came, invaded us. Invade, it became capture, land, conquer, mind, from. You can see all the special words like I have, everything is gone. See this? I is there, have is gone, right? The, you'll not be able to find out the anywhere, right? So whatever stop words were present over here, that all got removed, and then only we performed the stemming, right? Now you may be saying, Krish, the stemming does not look very good, right? So for that, what you need to do, I've already taught you with respect to snowball stemmer. So I will just import this, okay? And it is very much simple. I think you can do the same task again. So snowball stemmer, and then I will try to import this with respect to English. And obviously after this, you'll be able to get a good sentence, right? So let me just remove this one. So snowball stemmer, I've already done it, and I'm going to copy the same thing. Okay. And here I'm just going to say apply snowball stemmer, stemming, right? And then instead of stemmer, I will just write this word, that is snowball stemmer. That's it. Yeah. And now once I execute it, let me go back to the sentences, because that sentences have got changed now. So where is the sentences? Let's see. Okay. This is the sentences I've got executed now. Now I'm just going to execute this. Now, if I probably go and see my sentences here, you can see that now it is good, right? Now, one more important thing that Snowball has done. See over here, I still have capital letters, right? Like there may be some of the sentences which may be in small letter it also. So that becomes a repeated word. But since this is a capital letter, it will be considered as a separate word, right? For the model to understand, right? So what it does is that Snowball, one more advantage is that it is making sure that all the letter is becoming small, right? So all the letter is becoming small, and for some of the words, it is not even giving a good result, like poverty has become poverty. But if you try to do this with the help of lemmatization, you can also get a good word. Now let's try it with the help of lemmatization. So I'm just going to do the same thing. Okay. I hope everybody has understood with respect to snowball stemmer. Now what I'm going to do is that again, going to go back to my lemmatization code. So I'm just going to import this nltk.stem. And it is very simple, guys. I think we are just repeating things so that you also practice in a better way. Okay. So here I've got the WordNet lematizer. I'm going to initialize it. Perfect. This is done. Now I'm going to go ahead and copy the same code, right? And I will just write it over here. And instead of writing snowball, I'm just going to copy this. I'm going to paste it over here. Perfect. So I've done it, but let me just go ahead and execute the sentence part again, because I need to get the updated sentence. So I think it is somewhere here, paragraph. Okay. And here is the sentence. Okay. Perfect. Now let me just go ahead and execute the same thing. And now if you, okay, I'm getting has no stem. Okay. Sorry, it should be lemmatize. Okay. So lemmatizer.lemmatize. Now you see some time it took, right? Because it is basically checking from the entire corpus. Now if I probably go and see the sentences, now you have all amazing things with respect to words that are coming up correctly, and all the things are here, right? So with respect to this, you are able to get some good thing. Now one more thing you can do is that after this word, you can also put the post tag. Now if you put the post tag to V, right? Now you see what will be the output. You'll get a better output, I guess. Because most of the words it will be basically considering as, as an adverb, as a verb. So, but anyhow, we will try to understand about post tag again, more things, right? So I3 visions India in 3000 years history, people come, world come invade us, capture land. So all the stop words has got deleted. Now we are getting a very good one, at least better than stemming, okay? And the other one, that is snowball stemming, right? So this was the entire process with respect to text pre-processing. And here we have discussed with stop words and how you should also go ahead and do the text pre-processing. I hope everybody got that idea. Now in lemmatization also, you can see that it is not lowering it. So what you can actually do is that you can basically lower all the sentences, right? So let's say if you write sentences of I is equal to sentences dot of I dot to lower, right? So you can basically give to lower. Let's see whether it will work or not. Let's see whether it will completely work or not. I'm not sure whether dot to lower will work with respect to list, but I think it should work. I'm just going to execute this again, go down, okay, and apply this lemmatizer. Okay, str object has no attribute to lower. Okay, it's okay, not a problem. What I'm actually going to do, I'm just going to comment this, and before writing here, I'll just say word to lower. Okay, you have to definitely try different things, okay? And it's all about Google, just Google it, you'll be able to get it. So again, I'm going to execute this, and now I think it'll execute. I know I'm doing a lot of up and downs, but just try to follow the lecture. String object has no attribute to lower. Why? To underscore lower is there. To lower. Okay, let me just see. Str to lower case, right? Python. Let me just see this. It's okay if I don't have any other way to see it, but I think dot lower will definitely work. Let's see. Dot lower. Okay, perfect. It has worked now. Now if I go and see the sentences, it is done. Okay, so I don't have any regrets to search in the Google. You should also do the search in the Google. So now here you can see all the small letters are there along with the lemmatization. So we are going to continue the discussion with respect to NLP. And in this video, we are going to discuss about something called as parts of speech tagging. Now, I hope you have understood in lemmatization, this parts of speech tagging, it plays a very important role. Because if we are giving it as a verb or a noun, right, based on that, we are able to get the root form of the specific word, right? And we had seen a lot of examples with respect to this. In this video, we'll try to understand that how many different types of parts of speech tagging is there. And with respect to that, we'll also see a practical example. Let's say that if I am actually getting a sentence like this, Taj Mahal is a beautiful monument. How with the help of NLTK, we are able to understand that, and you'll be seeing that the output of this, let's say I'm just taking this particular example, the output for this will be that Taj Mahal will be considered as a noun, beautiful may be considered as an adjective, monument can be considered as a verb, right? I'm just giving as an example, but we'll definitely see this particular example, and we'll also see some extensive example altogether. Now, with respect to parts of speech, how many different types of things are there, right? So here you have something called as CC, coordinating conjunction, CD, cardinal digit, DT, determiner, EX, existential there, FW, foreign word, IN, preposition, JJ, adjective, JJR, adjective. So that basically means, suppose if I'm giving a sentence, automatically it will be able to categorize in all this specific different parts of speech automatically with the help of NLTK. And similarly, there are a lot of things over here. You can say personal now, personal pronoun, like for the letters like hi, he, she will be put up as PRP, right? It will be getting a tag called as PRP. If you see over here some more example like RB, adverb, right? Words like very, silently will be put up over here. RBR, it is also an adverb, but it will be like a comparative one, right? So example like better. So you have RBS adverb, like this you have lot, right? So what I'm actually going to do is that I'm going to take a very good example, and one assignment you just have to do is that take this particular simple example and try to find out and try to write down the comment in the comment section. Okay. Now over here, you'll be able to see that I have this particular speech of Dr. APJ Abdul Kalam, and obviously the same example I have shown you in the stop words example itself, right? So I'm going to take this, Very simple. Okay. And then let's consider that in this parts of speech tagging, I really wanted to perform stemming, let's say, but I don't want to perform any stemming because I want to see for each and every word, right, what kind of post speech tagging will be there. So no need to import all these things. Okay, so I'm just going to remove all these things. Instead, I'll just be focusing on importing NLTK. So I'll write import NLTK, and then here you can see that I'm just writing NLTK.send underscore tokenize. So that basically means I'm actually converting the paragraph into sentences. So let me just execute this, and once I get it here, you'll be able to see all the sentences. So in this example, I'm trying to show you that how for each and every word we'll be able to find out the post tag. Okay, so the next thing is that now what I'm actually going to do is that apply the stop words. Okay, and no need to apply the stop words also because we don't want to remove anything. So I'm just going to uncomment all these things, and I'm going to say that we will find out the post tag. Okay, find out the post tag, right? So this is perfect. Till here we are going good. Right now, what I'm actually doing over here, it is very much clear, very much easy to understand that over here we are able to do that. Like I'm just simply putting a for loop over here with respect to all the sentences, and this sentences here, what I'm doing is that I'm just trying to convert this into words. I'll be getting a list of words, and now no need to do the stemming. So I'll just remove the stemming. Okay. And over here, I'll just add this W word itself. I'll be getting the word. And I'm just saying that if the word is not in, set stop words dot words of English. So let's see that. Okay, I told you that I'll not apply stop words, but let us just remove the stop words because some of the stop words will not be playing an important role. So in order to do that, I'll just import all the libraries with respect to stop word, and obviously over here I had already written that, but let me do Control Z. So here it is stop words with respect to this, and I will also remove this. Okay, so two things, and I will just import the stop words. So I'm writing that from nltk.corpus import stop words, and now let's apply for this same thing, whatever we have done in the previous time. The same part we are actually repeating it. So here you can see that for word in words, if word not in this particular stop word with respect to English, I'm going to take all the words, and then I'm just going to comment down this code because I'm not going to join them back into the sentences because I need to understand what post tag each word will be getting. So I will basically write print. Okay, so here I'm just going to write a simple print statement, and in this particular print statement, before printing this also, what I can do, I can write basically this in the next line. Here I'll be using something called as nltk.post tag. Okay, so here you'll be able to see post tag. I can also apply it for words, and I can also apply it for sentences. Right now I'm just going to apply this for the words itself. So this is my entire thing, and here I'll just create a POS underscore tag variable. So this will basically indicate that everything is getting stored over here, and with respect to that, I'm just going to print this. Now let me revise it again, what all things we did. I'm iterating through each and every sentence, and then I'm converting this particular sentence into words, and for each words I'm applying stop words. Initially I thought that I'll not apply, but let's apply the stop words because see, at the end of the day, they are so small words like isn't, the, he, she. I don't want this particular words, right? So I'll remove the stop words, and I will take all the list of words over here. I did not apply stemming because I really need to find out whatever words are present over here. It needs to be like this NLTK will be able to find out all the different types of parts of speech tagging with respect to that. And then I just apply this particular simple code, that is nltk.post underscore tag of words, and then finally I'm printing it. So here you can see, I'll just execute it. I'm getting some error. I'm not going to make sure that nothing, I'm not going to, like, if there is an error, I'm not going to edit the video. So here it says nltk.download average perceptron tagger. So I definitely require this particular tagger to apply post tag. So what I will do is that I'll just go and copy and paste this. You also have to do this because you will also face this particular error. Now here you can see that it has been downloaded. Now if I probably go ahead and run it, now here you'll be seeing for the first sentence, I is basically a PRP. PRP basically means what? So if you probably go over here and see personal pronoun, and I had given the examples like I, he, she, right? Similarly, you'll be able to see that other words like three is CD, vision, NNS, India, NNP. Let's go ahead and see what is NNP. because India has been categorized with NNP. So NNP is nothing but proper noun, singular. It's like a name, place, it can be monuments, it can be different things. Like NNP, S is proper noun, plural, Americans, Indians, like that, right? So all those things are there. And how easily it is being able to simply, just show the post tags, right, with the help of NLTK. This is an amazing thing. And here with respect to all the sentences, you'll be able to see this, okay? And that is how powerful NLTK is. Let me just show you whatever assignment that I had actually given you, right? So this was a sentence over here. I'm just going to copy this and I'm just going to take this entirely, okay? And let's see whether we'll be able to do it. So I'm just going to use NLTK dot post tag sents. Now let's see with respect to sents also if you are able to do this or not. So I'm just going to put this Taj Mahal is a beautiful monument and I'm going to execute this. Now here you can see T. Okay, now in this particular case, what has happened, each and every word has been considered over here, right? This should not basically happen. So what I'm actually going to do is that I'm going to basically use post tag. Let's see what is the output with respect to this. So here also the same thing is coming. So the simple way in this particular scenario is that, again, I'll put a for loop for I in, okay, I'll say sentence or I in this entire quotes. I will just put this. I'll go through each and every word over here, okay? And I can write dot split with respect to this, because if I'm just using this dot split, this is my string, okay? And if I probably use dot split, you'll be able to see that what I'm getting, Taj Mahal is a beautiful monument, right? So for I in this, and here you can see that I'm iterating through each and every things, right? Each and every word. So I'm just going to print NLTK dot post tag, and I am actually going to use this. So here you can just go ahead and write this specific I, or instead of writing this I'll just write words, okay, for word in this NLTK dot post tag. I'm just going to use this specific word. Now here still there is an issue because I am iterating through each and everything. So if I probably get this entire thing with respect to the list, you'll be able to see, okay, let's see. There's something. Again, I'm not going to delete it. I'm just going to see what is the word over here. So I'm getting this, okay. And if I take this NLTK dot post tag with respect to this specific word, okay, this is the problem. Let's see, what did I do over here? I need to provide a list of words, okay, and then I'll be applying this. Okay, this is the problem. Okay, now all you have to do is that I don't have to give word by word. If it is giving word by word, here you will be able to see for every single character it is giving this, right? I really need to provide the list of words. So if I probably just copy this part and put it over here and remove all these things. Now what I have actually done after this error, see, I'm not editing this particular video with respect to this error, because you really need to see all these errors. In short, when I give like this, I'll be getting a list of words. So if I execute this here, now you can see that Taj, it is showing NNP, Mahal NNP, is VBZ, ADT, beautiful, JJ, monument NN. Now see, what did I do over here? Post tag basically, whatever parameter we give, we should be giving in the form of list of words. And if you are able to do that, we will be getting the same answer, right? So guys, I hope you are able to understand parts of speech tagging. I definitely got some errors, but I really wanted to show you all the errors that we are getting. Hello guys, so we are going to continue the discussion with respect to natural language processing, and in this video we are going to discuss about name entity recognition. This is an amazing topic. So let me open a file over here. So here you can see that, let's say that we have a lot of sentences, right? Like one example of this particular sentence is over here. The Eiffel Tower was built from 1887 to 1889 by French engineer Gustave Eiffel, whose company specialized in building metal frameworks and structures, right? Now this is a sentence. Now from this particular sentence, we know that what is parts of speech tagging, right? Which is noun, pronoun and all. But along with that, with the help of NLTK, we will also be able to get something called as name entity tags, right? Now, what are some of the examples of name entity tags? So here you can see one of the tag is something called as person. The second tag can be location or place. Third tag can be date, time, right? And here also I have given some examples. So if I probably say Eiffel Tower, it may be coming as a place, it can come as a location, right? Over here you can see that, okay, Gustave Eiffel, this will basically be getting tagged as a name itself, right? Here, suppose if this numbers are actually there, it can be something else, right? Suppose if we are giving some money value like $1 million. So let's say this $1 million is present somewhere here, right? And that will be basically tagged as something called as money, right? So it will be given some kind of name entity tags, right? So let us see some examples and let us see that how this name entity recognition will be given with the help of NLTK library. To begin with, what I'm actually going to do, I'm going to take this particular sentence, I'm going to go just execute it over here, okay? And again, we'll be going like how we did in the past videos itself. So let me do one thing over here. Let me create some more cells, okay? Now the first thing, I will just go ahead and import NLTK. And as you know that with respect to NLTK also, I can use something called as word tokenize. Word tokenize, word underscore tokenize, and here I'm just going to give all the complete sentence itself. So here let's go ahead and give the sentence over here, and once I execute it, here you will be able to see that the Eiffel Tower was, everything is coming over here. So this is my entire words, the list of words, right? So this is my entire list of words. Now perfect. Now see this. Usually for doing the parts of speech tagging, what do we do? We basically write NLTK dot post underscore tag, and I basically give this entire words to this, and based on this, each and every word will be assigned to some tags. Okay, so let me just write this is as my tagged elements or tagged something. I'm just giving a variable name which is like tagged elements, and this will get stored over here. Okay, now see this. If I really want to provide some named entity recognition, all I have to do is that use this NLTK dot named entity. So there is something called as NE. Okay, so let me just show you NE chunk. Okay, so NE chunk is a function over here. And if I probably see the definition of this particular thing, function, you'll be seeing use NLTK currently recommended name entity chunker to chunk the given list of tag tokens. Okay, and inside this, I will just pass all my tagged elements. Okay, so this will be my tag elements. I'm just going to give this. Probably we may get an error. The reason is that because we need to download this one, right? So here you can see that NLTK dot download maxnet any chunker, because here we are specifically using some chunker techniques to basically get the named entity, and for that we really need to download it, and that is what is the first requirement. So here you can see that I'm downloading it, and once this downloaded gets once this entirely max and any chunker gets downloaded, we are good to run this specific code. So this may take some amount of time because this may also be a huge it can be a huge library inside it which will needs to be downloaded. So now I will just go ahead and execute it. Still I'm getting some error. It also says that okay, you need to download NLTK dot download words. Perfect. So what I'm actually going to do, go and make one more cell, and please don't worry whenever you get some errors. I've seen some people who gets worried. First of all, just go ahead and see the error, what exactly it is. It is very much simple, and you just need to execute it. So guys, now once this NLTK download of words gets downloaded, now all I have to do is that over here you will be seeing that NLTK.NE underscore chunk. I have to give the tag elements, and then I just need to write dot draw. Once I execute this, here you'll be able to see this. What an amazing graph I'm able to get. Now see this, everybody observe this. I don't know whether you are able to see this properly or not, but just clearly if you will be able to see it, it has given most of the information very much clearly. So here it is very much clear that this entire sentence, right, the organization is recognized for Eiffel and Tower, right, which is a noun, right? Over here you can see this word was is a VBD, built it is over here, 1887 is something like CD, and here you can see GPE, right, French JJ, right, it is being able to determine as JJ. Here you can see person information is being able to get captured, which is like Gustav NP. So here you can clearly see all this information very nicely, right? So whichever entity is been able to get recognized, here you'll be able to find that. So person is there, GPE is there, and organization is there. That is what we will be able to find out. This S is the entire sentence over here, but with this graph you'll be able to understand that you're able to get the entire information. So like this, if you probably go and see that what all other entities you can find: person, place, location, date, time, money, and all. So I hope you were able to understand about named entity recognition and how you will be able to see this and how you'll be able to see the diagrams. So yes, this was it with respect to this particular video, but understand that NLTK provides this amazing feature. You should definitely use it where it is required. Hello guys, so we are going to continue the discussion with respect to NLP. We have already seen that. Now what is our next step, after text pre-processing, where we have specifically performed stemming, lemmatization, stop words, and we have cleaned the data, right? Now the main thing is that we really need to convert the text into vectors, and there are multiple ways. The first way that we are going to discuss about is something called as one-hot encoding. Okay, now we'll try to understand how with the help of one-hot encoding we are converting the words into a vectors itself. So let's take this specific example. So here I have a text and a specific output, right? Our main aim is that first of all we need to take this particular text and we need to convert this into vectors. Okay, now with respect to this, obviously I'm also not going to again lower all the sentences or words, but let me focus more on like how you can basically implement this one-hot encoding and what is the theoretical intuition behind it and how the vectors are actually created. So to begin with, over here, let's say that this is my text. The document one is the food is good, the food is bad, pizza is amazing. Okay, so this is basically pizza is amazing. Okay, now how do you find out how many unique vocabulary is there? Because see, the unique vocabulary will play a very important role, okay, while creating your vectors. Okay, so to begin with, what I'm actually going to do is that we just need to find out how many unique words are there. So let me go ahead and write it down. And obviously, you know that if I combine all these three documents, it becomes a paragraph or corpus. So let me just go ahead and let me just write down all the unique documents. So the is one unique, vocabulary. The is there, food is there, right? Is there, right? And good is there. So over here you can see good is also there. Then from the second sentence, you can see the food is getting repeated. So I'm just going to write bad. Okay. And if I go probably to the third sentence or the documents, here you'll be able to see pizza is there, which is a unique word or unique vocabulary. Is again getting repeated. And finally, we have something called as amazing. So all these words that are probably present over here, these are my unique vocabulary, right? Vocabulary. So these are just nothing but the unique words that are available in this entire paragraph or sentence or in this particular data set. Now, based on these unique words, one-hot encoding means what? Okay. Now let's say if I probably consider this particular document one D1. Okay. So let's say this is my D1. Now what does D1 do is that, like, if we are probably applying one-hot encoding, we will convert all these specific words into this vector representation. That basically means, let's say if I'm considering the word, then the vector representation for the word will be 1, 0, 0, 0, 0, 0, 0. Why? Because 1 is present over there. That basically means the is present in this specific word. So this is basically becoming 1. If I consider for the next word, that is food, then how we'll be able to represent it? It will be 0, 1, 0, 0, 0, 0, 0. Right? So here clearly you'll be able to see wherever those specific word is, it will be represented by a vector which will be of a dimension v. Okay. Now what is this v? V is nothing but the words that are present over here. So here you'll be able to see 1 word, 2 word, 3 word, 4 word, 5 word, 6 word, 7 word. So the unique vocabulary, I have 7. So it is going to be represented by the 7 vectors, where for those specific word it will be represented as 1 and remaining all will be represented as 0. Right? So now if I probably consider how can I represent this D1, that is the food is good, with respect to this particular vectors. Okay. So now understand that in this particular food, there are 4 words, right? 1, 2, 3, 4. So over here with respect to D1, the first word will have a representation of 1, 0, 0, 0, 0. So how many zeros are there? 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, right? So this will be my first word. Okay, then coming to the second word. Now the second word over here is food, right? So here you'll be able to see 0, 1, 0, 0, 0, 0, 0, right? So this will be my second word. Now if I come to my third word, it is basically is, right? So is basically represented by 0, 0, 1, 0, 0, 0, 0. So this is my third word. And coming to the fourth word, which is good. So here it will become 0, 0, 0, 1, 0, 0, 0, right? So this is my sentence one hot code representation with respect to this particular text. So this text, if I apply one hot encoding, I'm going to get this kind of representation. So guys, now if I talk about the shape of this D1 sentence, which has 4 words, right? So here you can see the first word representation is this one. The second word representation is this one, vector representation. Third word vector representation is this one. And fourth word vector representation is this one. So if I probably see the shape, right, it is basically 4 cross 7. 4 words, 1, 2, 3, 4. Okay. And 7 vocabulary size, right? 1, 2, 3, 4, 5, 6, 7. Okay. Now what we are going to do, we are also going to do the same thing for D2. Okay. So let's go ahead and try with respect to D2. I would suggest just pause the video, try it by yourself, and then probably continue the video. Anyhow, I'll be showing you the entire representation again. Okay. So over here, you'll be able to see that, which is my first word. Again, in D2, I have the food is bad, right? So again, these two are same. These 3 words are same. So I'm going to basically write the same representation. It will be 1, 0, 1, 0, 0, 0. I think there are 6 zeros. 1, 2, 3, 4, 5, 6 zeros. Okay. So this will be my first word. Coming to the second word, this is this one. Okay. I'm just going to write this over here. Okay. So this is my second word. So here I'm going to write 0, 1, 0, 0, 0, 0. I hope the size is 7. 1, 2, 3, 4, 5, 6, 7. Perfect. So coming to the third word now, here you'll be able to see 0, 0, 1, 0, 0, 0, 0. Okay. Now here you can see this food is, it is a similar word like D1 only. So the first 3 is just a replica. Coming to the last word, right? Now if I say last word, over here you can see good, over here you can see bad. Now whenever you have bad, this particular word will become 1, right? So you'll be having 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 1, 0, 0. So I'll just go ahead and write 0, 0, 0, again 0, 1, 0, 0. Perfect. So this is how the D2 is basically represented. And again, over here you'll be able to see the shape will be somewhere around 4 cross 7. Okay. Now, this was the technique, simple technique of one-hot encoding, like how we converted a text into a vectors. Over here, you can see each and every word is basically represented by a one-hot encoded based on the vocabulary size, whatever the vocabulary size is basically present. So here you can see that I have a vocabulary size of 7. So based on that, one-hot representation is given for each and every word. Okay. Now, going forward in the next video, we are going to discuss about all the advantages and disadvantages of this. And again, one-hot encoding is not getting used for this NLP use cases. We have techniques like bag of word and TF-IDF. We'll also understand what are the advantages and disadvantages, why should we not use this, and then we'll be trying to understand the bag of words and TF-IDF. Okay. Hello guys. So we are going to continue the discussion with respect to one-hot encoding and NLP, and I hope you have understood that how we can convert words into vectors, and probably the entire process I have actually explained to you over here. In this video, we are going to talk about the advantages and disadvantages of using one-hot encoding. So let me go ahead and let me write it down. So here are the advantages. Okay. And here are the disadvantages. Okay. Now, first of all, the basic advantage is that it is very easy to implement with Python programming language, right? Easy to implement with Python. Now, why I'm saying you that? Because in sklearn, we have a specific library where we can easily implement this, and it is basically called as one-hot encoder. Okay. And in pandas, if you're familiar with pandas library, we have something called as pd.get_dummies. Right. So this function will basically help you to create this entire one-hot encoding based on the words, right? And again, the second advantage, and obviously we'll see this kind of examples as we go ahead. But again, I'm not going to implement specifically separately as a video in one hot encoding because we don't mostly use this NLP in NLP technique, and I'll tell you why, because there are a lot of disadvantages also. Now let's go ahead and talk about the disadvantage. The first disadvantage over here, you see that over here at the end of the day, if I probably consider, right, the food is good, right? At the end of the day, I'm getting 1 0 0 zeros, and for the next word, I'm getting this 0 1 0 zeros, and there's so many number of zeros and ones. In arithmetic, in linear algebra, we basically say this as sparse matrix. Okay, so this basically creates a sparse matrix, right? Now, what is sparse matrix exactly? To talk about sparse matrix is that in an array, in a matrix, you have a lot of ones and zeros. Okay. And what is the problem with respect to sparse matrix? I can also say this as, we can also convert this into an array also. So we can also say this as sparse arrays. But understand what is the disadvantage with respect to sparse matrix. Whenever we apply any machine learning algorithm, this specific machine learning algorithm, after we convert the text into vectors, right? In most of the machine learning algorithms, this leads to something called as overfitting. Right? Now, what exactly is overfitting? Overfitting is a process wherein you get a very good accuracy with the training data, but with respect to any new data, it will not be able to give you a very good accuracy. So this sparse matrix usually leads to something called as overfitting, right? So this is the one of the major disadvantage. Now let me talk about the next disadvantage over here. Okay. Now over here, let's say that I have this words like the food is good, the pizza is the food is good, the food is bad, pizza is amazing. Right? Now see one thing over here, right? In any machine learning algorithm, whenever you give the data, right? And in this case also, if I probably say this vocabulary, right? These are all my features. The food is good, bad, pizza, amazing, right? Now over here, you can see that most of the time, my inputs for every word that is getting converted into a vector, the size is 7, right? 1, 2, 3, 4, 5, 6, 7, right? And based on the number of words, here you will be seeing that I'm having 4 words, so I'm getting 4 cross 7. Here also I'm having 4 words, which I'm actually getting 4 cross 7. But if I consider with respect to the third statement or third sentence, right? So if I probably consider D3, right? And if I start creating a one hot encoded format for this, so what it will be? See, pizza is there, right? So pizza, where it is 1 at this particular instance. So I will probably create something like this 0 0 0 0 0 1 0, right? So this is pizza, right? Is, again we have is over here. Is nothing but this will be 1 and remaining all will be 0. So I'll just write 0 0 1 0 0 0 0, right? And the third statement is amazing, which will be the last one as far as I remember from the vocabulary. So this is how my D3 looks, right, in one hot encoded format. But one thing you really need to understand. Over here, the size is 3 cross 7, right? Now in machine learning, you need to understand one thing. Whenever we perform NLP or let's say any machine learning use case, the number of features should be fixed with respect to the length. But here you can see this is 4 cross 7, this is 4 cross 7, this is 3 cross 7. So I cannot train this particular data for a machine learning algorithm because over here we still don't have a fixed text size, right? So this is one of the major disadvantage unless and until, and with the help of one hot encoding, we are not getting a fixed text size, right? Over here I've got 4 cross 7, 4 cross 7. If this was also 4 cross 7, I could have trained it, right? So over here, I'll say that for ML algorithm, we need fixed size. We need fixed size input, right? And right now it is not there. So this is again a major disadvantage, right? We'll be seeing in the upcoming lectures how with the help of bag of words, TF-IDF, we'll be getting a fixed size of words. Okay. Now the third one that you'll be seeing. Most of the times we are finding zeros and ones, right? Zeros and ones. In zeros and ones, most of the times, if a specific word is there, that will become 1 and remaining all will be 0. But if I talk about the semantic meaning between these two words like the and food, right? we are not able to exactly calculate like how far, how equal it is, or how similar that specific word is. And this process is basically called as semantic. So here I will say that no semantic meaning is getting captured. No semantic meaning is getting captured. Now let me talk about this in a very good example. Okay. Let's say I have something like this: food, pizza, burger. Okay. Now you know that, let's say that in my vocabulary I have 3 words. So for the food representation, I will basically write it as 100. For pizza, let's say I'm going to write it as 010. And for burger, I'm just going to write it as 001. Now understand, these are my vectors. And right now, since there are 3 features, I'm basically having 3 vectors. Now, if you have probably heard of something called as cosine similarity, or if you really want to find out the distance between this vector to this vector and then this vector to this vector, if I probably consider this, let's say I'm just going to draw a 3-dimension. Okay. Let's say this is being determined by something like burger, and this is being determined by something like food, and this is being determined by something like pizza. Now, if I talk about all these things, right? Like, let's say in case of food, it is 100. So in this axis, I will probably be getting 1. So this will be represented by 1, 0, 0 in 3 dimension. And if I talk about pizza, 010, so this will be my another point. Let's say I'm just going to denote this by another point, 0, 1, 0. And let's talk about the third point over here. The third point will be somewhere here, burger. It will be in the same distance. So this will be 0, 0, 1. Now, if I probably calculate the distance between all these things, it will almost be equal, right? So it is not being able to tell the exact difference between food, pizza and burger. It is obviously considering that, okay, all these words are in equal distance. So we cannot understand that how this particular word is different from this, right? This is super important to understand. So in short, what I am actually trying to say over here is that no semantic meaning is basically getting captured. That basically means in this particular sentence, I'm not able to understand which is the most important word, how this word is related to this word, or how this word is much more similar to this word. So that information is not getting captured, because at the end of the day, I'm getting ones and zeros. Okay. So this was the third major disadvantage. Now talking about the fourth disadvantage, and this is also very super important. And this particular concept is something called as out of vocabulary. Out of vocabulary. And what does this basically mean? OOV. Okay. Now what is this all about? Let's say that right now I have this many vocabularies of word. Let's say after I train my model, now I want to test it for my new data set. So for testing on my new data set, this will be my test data. Let's say I will say burger is bad, and I need to predict this. So this is my test data and I need to predict this. Now you know that over here with respect to this particular sentences, okay, burger is nowhere present in this particular vocabulary. So what will be the problem? We will not find out a way, we will not have any way to represent this burger in the form of vectors, right? We'll not be able to form a vectors over here because anyhow we don't have a vocabulary word. So what will happen in this particular case? And obviously we'll not be able to perform this one-hot encoding because in our vocabulary, I just have this many number of words. So this will not work when a new word is actually coming, wherein it is not present in the vocabulary with respect to the test data. And obviously this is again a major disadvantage, right? So this technique is basically called as out of vocabulary. So this was in short about the advantages and disadvantages of this. Understand sparse metrics basically means many ones and zeros. It leads to overfitting with respect to various machine learning algorithm. Then for any machine learning algorithm, I definitely require a fixed size input. Right now, we are not able to get it. That basically means all my sentences should be of fixed size. It will not work. No semantic meaning is getting captured. I've already told you, because if we try to calculate the distance, all these words are equidistant. It is not saying that whether pizza is very much similar to food or burger, how much similar it is to food, right? That similarity is not there. And based on that, semantic meaning is not getting captured because here either we are getting ones or zeros. So we are not able to provide, right? Over here, you can see that much more maximum information, which is the most important word. That information is also not getting captured. So this was in short about the advantage and disadvantage. I hope you have understood this. And again, the next technique with respect to converting word to vectors is something called as bag of words. We'll try to see that how it is fixing some of the disadvantage from here. And yes, one more major disadvantage I'll say you that, let's say that if you're right now, I just have 3 sentences. Let's say I have just 7 vocabulary. Let's say tomorrow I will be having 50k unique vocabulary size. Now what will happen in this particular case? Right, I'll be getting so many number of ones and zeros. So in short, again, this is actually leading it to sparse matrix. But in a real world scenario, I'll just not be having 3 sentences, right? I'll be having bigger sentences, and I'll also be having many sentences as such. So this is also one of the thing. In any interview, if they ask you, you probably need to talk about or explain like this with respect to advantage and disadvantage. Hello guys, we are going to continue the discussion with respect to NLP. In our previous video, we have already seen that we have discussed how one-hot encoding works, right? And if I probably talk with respect to different types of ways how we can convert a text into a vectors, we had completed already one-hot encoding. Now we are into the second, that is bag of words. Now let's go ahead and understand how bag of words actually work. And this is super important because this is the technique which you can do simple tasks like sentiment classifications or whether basically in short a text classification kind of task easily you'll be able to solve. Okay. Some of the applications, famous application like whether a mail is a spam or a ham, everything you'll be able to solve it. Now let's say that I have a data set, okay, and in this particular data set I'm just saying that this is a positive or negative statements. Now in this particular data set I have 3 sentences. Let's say he is a good boy, she is a good girl, boy and girl are good, okay. And all these are like positive statements. So the output of all this are ones, right? In supervised machine learning, we really need to know the output also. Now, let me go step by step and show you that how bag of words are implemented. So this is basically the step 1, right? I have the data set. Now let's go to the step 2. Now what happens in the step 2 is that once I go over here, right? There's multiple steps that actually occur. And initially we should also go with respect to this. The first thing is that if I probably consider 2 things are going to basically happen. First of all, we will lower all the words, and usually all the steps we will even be doing for all the other techniques also. First, we will lower all the words, and then we will probably apply stop words, right? And this also I have already shown you. Now, when I lower all the words, let's say my sentence 1, right? My sentence 1 now becomes, I'm going to take only this text data. I don't have to worry about the output, because later on, once we convert this text into vectors, we can apply it to the machine learning algorithm. So in the sentence 1 here, you can see as soon as I lower the words, what will happen? This all will become smaller. Now, why I'm doing this? Because there may be some repeated words. Now, in this particular case, the capital with capital B, you have boy. Here, small b, you have a boy. So both these words are same. But since it is in uppercase, this will be treated as a separate word. So we really need to lowercase all the words. So I'm just going to write lowercase all the words. Now in sentence 1, after lowering casing, so what will happen is that this all will become smaller letters. Then once we apply stop words, now what happens in stop words? These all words like he, she, is, a, it will get deleted, right? Because we don't require this particular word for any kind of task like sentiment analysis. Important words like good boy, good girl is basically required. So this all things will go like and, are will also go. Now what will happen with respect to this? The sentence 1 words will become only like this, good boy. Okay, I'm showing you step by step with the help of Python. When we do, with the help of libraries, when we do, it is very much simple. We don't have to worry that much about it. Okay, we just have to use one library. So sentence 2, what it will become once the stop words will get removed, it will become good girl, right? And similarly with sentence 3, I will be having this specific words, that is boy, girl, good, right? So all these things are there. I have sentence 1, sentence 2, sentence 3. Perfect. Now what we do is that we go ahead and calculate the vocabulary. Now how many words are there in this vocabulary? We have good, boy, girl, boy and girl, and again it is getting repeated. So if I probably consider how many unique words are there in the vocabulary, so I will be able to write it over. The first word is nothing but good. So I'll go ahead and write good. Good is my first word. And one more thing that I will probably write, that what is the frequency of this specific word, like how many times these words are there in different sentences. And obviously you can see 1, 2, 3. 3 are there, so I'm going to keep the count as 3. Then we have something called as boy. Over here you'll be able to see how many times boy are there. So in sentence 3 also boy is there, in sentence 1 also boy is there. So I'm just going to make the count to 2. And coming to the next one, which is called as girl. So again, girl word is also there in this vocabulary. And again, girl also you will be able to see 2 times it is there, right? Now, first of all, you need to see that in this frequency with respect to different vocabulary words, is this in ascending order? And obviously, is this in descending order? So maximum number of frequency will be put up in the first word, right? Then boy is present 2 times and girl is present 2 times. So this can be moved up and down. But just understand what I've done is that based on this descending order, I have just ordered all these words. So it is basically from maximum to minimum. Okay. So this is there. Perfect. Now, before applying bag of words, you already have seen that how many vocabulary size, what is the vocabulary size? The vocabulary size is 3, right? And I can see in a bigger data set, I can have this kind of words a lot. So I will be having all these words like this, and frequency will also be there. And one important step is that it is not necessary that you use all the words. This is also there in this bag of words itself. Let's say that over here in the vocabulary, there are 100 unique words. And let's say some of the words are just present once, right? So if some of the words are just present once, we even need not take that. So when we'll be doing the coding with respect to a bag of words, we also have an option that we just select the top 10 features or top 20 features, which of the words are getting repeated more and more. And that is the importance of this particular frequency. Okay. Now, perfect. We are till here. Now, the next step will be that it is very simple now. Based on the topmost frequency, what I'm actually going to do, I'm going to keep these words as my feature. So good will come over here, boy will come over here, and girl will come over here. Okay. Now, you already know what is the sentence 1, right? So sentence 1, what will happen is that this sentence 1 has good boy. Now see how this will get converted into a vectors. Wherever good is present, that will become 1. Wherever boy is present, that will become 1, and remaining will become 0. So this entire sentence you'll be able to see that it is getting converted to 110 as a vector. Okay, so this was the text. Now this is getting converted to 110 as a vector. Now similarly, if I go with respect to sentence 2, wherever there is a word like good, that will become 1. Wherever there is a girl, that will become 1, and remaining all will become 0. I'll talk about the advantages and disadvantages why we are doing this. Previously, in One Hot Encoded, you saw that for every word we are doing this. For every word, we are creating a vector. But here, for the entire sentence, this vector is coming. Okay, and there are a lot of advantages when I talk about this, which I'll discuss. First of all, let's understand what or more we'll be having in this. So S3, you'll be able to see the sentence 3. Here I have boy, girl, and good. So wherever boy is there, that will become 1. Girl is there, that will become 1, and good will be there, that will become 1. Okay. Now, this is my entire vectors, and obviously I will also have my output variable. The output variable can be 1s, 0s, anything as such, right? If you are probably solving the sentiment analysis or something like that. Okay. Now, these are my entire vectors. Okay. And this is the vector for the entire sentence. Okay. Entire syntax. And this is how the entire bag of words converts a text into a vectors. Okay. Now what we can do is that we can take this particular vectors, we can train with an machine learning model, and we'll be able to get the output. Now one more important thing that I really want to put. Let's say that I have a word over here, right? Good, girl, girl, right? So let's say if I have one more word like good. Now in this case, what will happen? Okay. In this case, what will happen? Usually in bag of words, since good is repeated 2 times, so I will increase the count to 2. Okay, in this particular case. So what I'll do, I will increase the count to 2. Okay. Now there are 2 things. One is binary bag of words, and one is normal bag of words. Now in the case of binary bag of words, even though the count is 2, what it is going to do, it is going to force it to become 1. So most of the time, if the word is present, it may be present any number of time. The value is either 1 or it is 0. And in normal bag of words, I can increase the count to 2, 3, 4 based on the number of words that is there. So that is the basic difference between binary bag of words and bag of words. That basically means here you'll be having only ones and zeros, and here based on the frequency, count will get updated. Count will get updated based on frequency. So this is the basic difference with respect to this. Okay. So I hope you have understood like how with the help of bag of words we are converting a text into a vectors. Now in the next video I'm going to discuss about what are the advantages and disadvantages with respect to this, like how we have actually discussed in one-hot encoding. Okay. Hello guys, so we are going to continue the discussion with respect to bag of words. Already we have understood the intuition behind bag of words, how it is converting a text into vectors. Now as usual, let's go ahead and discuss about the advantages and disadvantages. So first of all, I will go ahead and write the advantages, and then I will go ahead and write the disadvantages. Okay. So and obviously we have also discussed about the advantages and disadvantages with respect to one-hot encoding. We'll try to compare with this and we'll try to see that what all problems is getting fixed. Okay. First of all, yes, again, this is easy to implement and it is intuitive. So I'll just write something like simple and intuitive. Simple and intuitive. Okay. The second point with respect to advantages. Now here what it'll do in one-hot encoding, you see that we have seen that some important thing is there in machine learning algorithm, right? Okay, with respect to sparse metrics I'll be discussing, with respect to semantic meaning, out of vocabulary, everything I'll be discussing. First let's consider this particular second topic, which is like for ML algorithms we give fixed size inputs. Now over here, with respect to bag of words, any statement, now here you can see that some of the sentence may be 3 words, 5 words, 10 words. At the end of the day, based on the vocabulary size, you are able to get all the sentences converted into that many number of dimensions of words. So here the vectors is getting fixed, the inputs are getting fixed because here our vocabulary is getting fixed. So this particular problem is getting solved. Okay. In one-hot encoding, you do not have a fixed size inputs since we are creating words for every vectors. Sorry, we are creating vectors for every words. Okay. So what we are going to do over here, the second point that you'll be seeing, yes, you have a fixed size input, right? And this will superbly help you for ML algorithms training. Okay. ML algorithms. Now this is the two major advantages. Now, if I talk about the disadvantage, see over here, the first disadvantage with respect to one-hot encoding is sparse metrics. And I've already told you what exactly is sparse metrics. It is just nothing but ones and zeros. Let's say if your vocabulary size is 50,000, then what will happen? Every sentence will get converted into, that size of the vocabulary, right? So still sparse metrics problem is there. So with respect to disadvantage, again, I'm going to write it as sparse metrics and array, or array is still there, and this will actually lead to overfitting. Okay. Now second major disadvantage again. See, at the end of the day, whatever statement that you have, like good boy, good girl, or it can be boy, girl, good. Okay, something like this. You'll be seeing that based on this sentence, right? And based on this vocabulary and based on the frequency of the vocabulary, the ordering of the word is changing. Now see, understand, if in a sentence, the ordering of the word changes, and based on that, this vector is getting created. Because see, based on the frequency, we have written all the vocabularies right over here. Good was present maximum number of times, so we wrote it as first. Boy was present in the second number, so we wrote it over here, right? And a girl was present for two times, and we have written it at the last, right? Now over here, you can see that if I probably consider the third statement, boy, girl, good, right? But here you can see that entire word is getting ordered, like it is completely changed, right? The ordering of the word is completely changed. So I'm having 110 for sentence 3, I'm having 111. Now when the word ordering is changed, the meaning of the sentences also gets changed. And because of that, some of the semantic information is not getting captured. I'll talk about more semantic information, but here you'll be able to see that ordering of the words is getting changed. This is super important. Ordering of the word is getting changed. Because if this is getting changed, the meaning of the sentences changes, right? Is getting changed. So this was the second disadvantage. If I probably talk about the third disadvantage, okay, third disadvantage, again, we'll go and see over here with respect to out of vocabulary. Now, what happens if I probably add a new word like boy, girl, good, and let's say I'm going to add something called as school. Now, here you will be seeing that the school word is not present in the vocabulary. So, what it is going to do for this specific word, anyhow, it is going to get rejected, right? It is not at all getting considered in this training data. Let's say that for our new test data, in our new test data, we have included a school word. And we need to do the prediction for this particular word with respect to output. So the first step will be that we'll do text pre-processing, and then we'll try to convert this into a bag of words using the same technique what we did in the training data set. But here you see that in my training data set, I do not have a vocabulary which is called as school. So what it is going to do, it is just going to ignore this specific word, and it is just going to see that where good and boy and girl are there. Right? So still, out of vocabulary still exists, because this word may be an important word for the sentence, but it is getting removed because we don't have that in the vocabulary. Right? Major problem. So yes, out of vocabulary is obviously an issue over here. Right? This still persists. Okay, OOV. Now this was the there. Now one more important thing. Semantic meaning in this is still not being getting captured. Why? I'll tell you. Semantic meaning is still not getting captured. And there are multiple things to explain this. Okay. Now, first of all, obviously, you know that I'm having either ones and zeros. Okay. Now, in this particular case, good and boy, they are getting the same importance. Right? For girl, obviously, if the word is not present, I'm getting 0. Small amount of semantic information is getting captured when compared to the one-hot encoding format. But here you say that when we have many vocabularies, either my values will be ones or zeros. One is just indicating whether the word is present or not. But which is the most important word? What is the most important context in that particular sentence? That is obviously not getting captured. And if that is not getting captured, semantic in turn will not get captured. Now, the other thing over here is that there is also a very important thing. Let's say that I'm having two sentences. Okay. It is like the food is good. Let's say in my data set, I have this sentence. The food is not good. Not good. Now, let's say I don't go ahead and remove all the stop words and all. For this, I will be having a vocabulary like one. Let's say all these words are there. Okay. And the is also a separate vocabulary. Food is also a separate vocabulary. Is also separate. How many unique vocabulary are there? 4. Because not is also there, right? So is will also become 1. Not will be 0. And good will be 1, right? So this is how we convert from this to this, right? Similarly, from here to here, if I really need to convert, then what will happen? 1, 1, 1, 1, 1. Because not is also present, so I'm writing 1. Now, let's say this is my vector 1 and this is my vector 2. If I try to find out the difference or how similar this vector is just by plotting some points. Let's say that I've converted this particular dimension to 2 dimension using PC and probably I've plotted it. Based on this, right, only one value is getting changed, is and not, right? So I will get both these vectors very much near to each other. And this we can basically do it through something called as cosine similarity. So let's say this is my vector 1. This is my vector 1. This is my vector 2. So vector 1 is basically present over here. Vector 2 is present over here. If it is near to each other, if the angle between them is very near to each other, or if the angle between them is very less, I may say that both the sentences are same, almost same or similar, right? This is almost similar. But do you think both sentences are almost similar? Because it is the complete opposite of them, right? But since there is only one word that is getting changed, because of that, only one of the values getting changed over here, right? Like zeros and ones are happening. And when we plot this, it is becoming kind of a similar word. But this should not be a similar word. This is completely opposite word, right? So this kind of situation is also not getting handled well with the bag of words. And later on, the techniques that we'll be learning, like word2vec and all, this will be solving all these problems, right? So I hope you are able to understand the advantages and disadvantages of bag of words. Super important with respect to interview. And if your basics of this is getting strong, trust me, you'll be able to understand bag of words, average word to vec. Sorry, you'll be able to understand word to vec, average word to vec in a very easy manner. And there are techniques in deep learning which is also going to come, which is called as embedding techniques, word embedding and all. All those will get solved in a very easy way, right? Hello guys, so we are going to continue the discussion with respect to natural language processing. In our previous video, we have already seen what is n-grams. Now what we are going to do is that we are going to see one more efficient way of converting a words into vectors, and we specifically say it as TF-IDF. Now what exactly TF-IDF is? It is nothing but term frequency and inverse document frequency. So we'll try to understand how with the help of TF-IDF we will be converting all these particular sentences into vectors. Okay, and I've taken the same example what we specifically did with bag of words like good boy, and this is after lowering all the character cases. Along with that, after performing or after removing the stop words. So I have sentence 1 as good boy, sentence 2 as good girl, sentence 3 as boy, girl, good. Okay, and this is the same thing, like from the same materials. If you will be able to see, I've done the same thing. I've taken the same thing over here. Okay, now there are two components in TF-IDF. One is term frequency and the other one is something called as inverse document frequency. So whenever I talk about term frequency definition or the formula, how we calculate it, it is given by number of repetition of words in sentence divided by number of words in sentence. Okay, I'll try to show you completely taking this as an example how we can calculate term frequency. And over here, inverse document frequency formula is very simple. We basically calculate it by inverse document frequency is nothing but log to the base E number of sentences divided by number of sentences containing the word. Now this is super important, and probably don't get confused with the formula right now. I will try to explain you each and everything. Okay, so let's go step by step and let's see how we can calculate the term frequency. Now first thing that I am going to make sure that what I calculate is nothing but I will be using this term frequency. Now with respect to this term frequency, you know that how many vocabulary of words are there. Okay, so first of all, I will just try to show you in a different way by creating a table. So I have S1 sentence, I have S2 sentence, and I have S3 sentence. Okay, and then with respect to my vocabulary of words, I have something like good. Okay, then I have boy, and then I have girl. And already we know that only 3 words are basically present in the vocabulary. I'm trying to show you with a simple example so that you will be able to understand how TF-IDF will work. Okay. Now the first thing, let's go back to the definition. Term frequency is nothing but number of repetition of words in a sentence divided by number of words in a sentence. So suppose if I take S1, and with respect to S1, if I really want to find out the term frequency of this particular word, that is good. How do I calculate? I just need to see how many number of times this particular word is repeated in the sentence. So here you know that it is repeated just one time. And then I will be dividing by number of words in that specific sentence. So it will become 1 by 2 because I have 2 words. Now let's go to the next word, that is boy. So boy is also present how many number of times? 1, and this will be divided by 2. Okay, I'll tell you why we are doing this, because when we understand the advantages and disadvantages, you'll get a clear idea about why TF-IDF will perform better than compared to bag of words. Okay, then I have the word girl. So girl, I know that over here it is not present, right, in the sentence 1. So it will be 0 by 2, so which is nothing but 0. Okay, similarly with respect to S2, here you'll be able to see how many times good is present, only 1 time. And the total number of words is 2, so 1 by 2. Boy is present 0 times, so it will be 0 by 2, which will be nothing but 0. And girl is basically present over here 1 time, so again I'm going to write 1 by 2. Now let's go with respect to the sentence 3. So sentence 3, how many times good is present? 1 time, and the total number of words now is 3, right? And then if I go next to see the boy word, how many times boy is present? Only 1 time. So this will also be 1 by 3, and girl will also be present 1 by 3 because the total number of words are 3. Okay. So this is how simple we are able to calculate the term frequency. Okay. Now let's go ahead and let's try to find out the inverse document frequency. So I'm just going to write over here as IDF. Now with respect to IDF also, we will be creating two fields, very simple fields. And remember, this will basically be my IDF. And this is with respect to my words over here. So my words are nothing but good, boy. Let me write it down in a better way so that it should look in the same order. So here will be my good, here will be my boy, and here the next word is something like girl. Now, in order to calculate the inverse document frequency, it is very much simple now. All I have to apply this log base E, right? How many number of sentences are there with respect to good, right? With respect to good, suppose if I really want to calculate the inverse document frequency of good, okay? So here what I'm writing, I'll write log base E multiplied by number of sentences. How many sentences are there? There are 3 sentences. So 3 divided by number of sentences containing the word. So good is present in all these 3 sentences, 1, 2, 3, right? So I will basically be writing log to the base 3 divided by 3. Okay. And if I basically calculate this, if you try to calculate it, it is nothing but I will be getting as 0. Okay. And you can basically do with the calculator. Boy, over here again, log to the base E, number of sentences are 3, and how many time boy is present? How many time boy is present in how many sentences boy is basically present? It is present 1, 2, right? Sentence 1 and sentence 3. So I will be writing log base E multiplied by 3 by 2. Similarly, girl will also be present same number of time. If you probably see how many sentences girl is basically present. Okay. So I have independently calculated term frequency and I have independently calculated inverse document frequency. This is perfect, right? Now, whenever we say TF-IDF, in short, what I'm actually doing, I'm multiplying this two, okay? Term frequency and inverse document frequency. I'm taking the combination of this two. Now, let me go ahead and write it down in a better way still, in the way that we specifically want, and finally how our vectors will look like. So this is my vocabulary, good, boy, girl, and this is the final TF-IDF, okay? So final TF-IDF based on this calculation, and this will differ based on dataset to dataset, okay? So first of all, with respect to sentence 1, whenever I see the combination of TF-IDF with respect to good, all I have to do is that multiply 1 by 2 with this 0, okay? So I'm going to multiply this with this. So in sentence 1, so see, this is the sentence 1, right? This entire thing is the sentence 1, right? So this is my sentence 1, okay? So I will be taking this combination and I will multiply with this, right? So sentence 1, good, 1 by 2 multiplied by 0, it is nothing but 0. With respect to boy, 1 by 2 multiplied by log base E, 1 by 2 multiplied by log base E, 3 by 2 will be the value that I'll be getting in sentence 1. And with respect to girl, 0 multiplied by this, it will be 0. Now let's go to the sentence 2. In sentence 2, I will go ahead and look for this now. Again, 1 by 2 multiplied by 0, again good will be 0. And this boy is nothing but 0 by 0. So this 0 multiplied by 0 is nothing but 0. And here I have 1 by 2 multiplied by log base E, 3 by 2. I will tell you the exact thing what we really need to know, why we are doing this specific thing. Everything will make sense. And it will make sense, and I'll make you definitely understand all these things, okay? So coming to the next one with respect to sentence 3. In sentence 3, I will do this multiplication with this, right? So 1 by 3 multiplied by 0, again it will be 0. 1 by 3 multiplied by log base E, 3 by 2. And 1 by 3 multiplied by log base E, 3 by 2. Perfect. So we have got all this calculation, and this is how my vectors will look like. So here you will be seeing that for sentence 1, we converted this entire sentence into vectors, which looks like this, right? So this is my sentence 1 vector, this is my sentence 2 vector, and this is my sentence 3 vector. And obviously I'll be having an output with respect to any kind of classification that I want to do. And then I will train my model by passing my sentence 1. So in short, if you see, good boy is basically converted into a vector which will look like this. Okay, this entire sentence 1 is getting converted into a vector 0, this and this 0. right? So again, you can calculate this with the help of calculator, but this is what is the way that we have actually done. We have converted all our sentences into vectors, and in TF-IDF, this is the phenomenon that is used in converting the words into vectors. Now you may be thinking, Krish, what is so special about this? We have got some values, okay, that is fine. And that is what I'm going to talk about in my next video about the advantages and disadvantages of TF-IDF. Hello guys, so we are going to continue the discussion with respect to TF-IDF, and already I've shown you how we can, what is the formula of TF-IDF, that is term frequency, and IDF, that is inverse document frequency. And I've also shown you an example over here, right? So till here, that is everything is fine. Now let's talk about the most important thing about advantages and disadvantages and why this is probably better than bag of words, okay? So first of all, the basic advantage that we have, again, this is quite intuitive. The implementation is also quite intuitive. Coming to the second advantage, okay? Like bag of words, here also our inputs are basically fixed size, and this is based on the vocab size, right? And this advantage is also present with respect to bag of words, that is also there. But the third advantage that I'm actually going to talk about, see, in bag of words also we had fixed size, right? But this third advantage is the major advantage. Now let's talk about the third advantage, okay? So the third advantage is that the word importance is getting captured. I'll explain you what exactly this is. Word importance is getting captured. Super important point, and probably they may also ask you this specific thing in interviews. Now, if I probably go and see my entire paragraph, let's say this is my paragraph, good boy, good girl, boy, girl, good, right? I'm getting a TF-IDF of this number, right? And over here, I have also written this with the help of bag of words. In bag of words, I used to get either ones or zeros. Wherever that word is present, that is coming as 1, otherwise it is 0 if it is not present in the sentence. But how the word importance is getting captured? Over here, equal importance is given to both the word, like good and boy, right? Because it is present in the sentences. But here it does not work like that. Here, considering the entire paragraph, what it is happening is that we are focusing on two things, term frequency and inverse document frequency. If a word is present in all the sentences, it should be given less importance. Understand this, okay? If a word is present in all the sentences in that paragraph, it should be given less importance. Why? Because all the sentences having that specific word, so it is not playing that amazing or important role. Word importance needs to be captured from every sentence. That is what we specifically want. Now over here, you can see that boy is there, right? Over here, girl is there. Now, boy and girl are getting repeated in 1 or 2 sentences, not in every sentences. So if it is not repeated in every sentences, we need to value this particular word in every sentences as such. So if I probably take an example of good, good is present in all these 3 sentences. So after we calculate TF-IDF, here you will be seeing that all zeros we are getting over here. Major issue, right? So not an issue, but it is a good thing. We are ignoring the good word because it is present in all the sentence. Now, if I consider with respect to boy, so sentence 1, boy will play a very important role now, right? So with respect to boy, here you will be seeing that I'm getting some values, right? I'm getting some values. Now in the second sentence, obviously boy was not there, so it became 0. But if I consider girl in the second sentence, so here you will be seeing that I'm getting some value. That basically means in this particular sentence, the girl word is super important, and the context is based on that specific word that we are having a value of TF-IDF, right? So in short, what is happening is that word importance is getting captured. And in the third sentences, it is talking about both boy and girl. So you'll be seeing that both this boy and girl has some values. So in short, we are capturing some word importance over here based on the context, right? Super important point. And by this, our machine learning model will be able to understand that, okay, something specific we are basically talking about. And that way the mathematical models will be able to find out what kind of predictions it actually wants. And through this, the accuracy increases. Now let's talk about the disadvantages. Obviously, in this particular case also, you have lot number of zeros. So sparsity still exists. Okay, sparsity still exists over here. And again, we will try to see how we can solve sparsity using word2vec. The second thing is that what we specifically discuss about is something called as OOV, out of vocabulary. Now here also, if I probably add any more words over here with respect to the test data, that is going to get ignored, because over here also all my features is basically made based on our training vocabulary size, right? So this is basically the advantages and disadvantages with respect to TF-IDF, but definitely just by seeing the advantages and disadvantages, we can definitely know that TF-IDF performs better than bag of words, right? Now, in the next video, we'll try to see some practical implementation with the help of NLTK and Python. And again, guys, you really need to practice this considering different data sets. We will try to provide you more assignments as possible so that you can practice these things also. Hello, guys. So we are going to continue the discussion with respect to natural language processing for machine learning. In this video, we are going to discuss about word embeddings. And this was probably the topic that I should have covered long back, but I'm deliberately keeping this particular topic at this point of time. Why? Because we have discussed so many topics wherein we focused on converting word into vectors. So now you'll be getting a very clear idea about what exactly word embeddings is. And here I've given you a Wikipedia definition. So this is a very simple Wikipedia definition. I have taken it from Wikipedia. So the entire credit goes to Wikipedia over here. So over here, you can see the definition that in natural language processing, word embedding is a term used for representation of the words, right? For text analysis, typically in the form of real valued vectors that encodes the meaning of the word such that the word are closer in the vector space are expected to be similar in the meaning. So let's say that I have two words, king and queen, okay? Or forget about king and queen. Let's say that I have two words and the two word is like happy and excited, right? Let's say I have this two specific word. Now, when I have this two specific word, with the help of word embedding techniques, what we do is that we convert this particular word into vectors. And let's say if I try to plot this vectors in a two-dimensional graph, okay? And if I really want to convert this into two-dimensional graph, we have techniques like PCA or other techniques, which is an unsupervised technique to do dimensionality reduction. So once I probably plot this, let's say happy and excited are coming near to each other. Based on this particular vectors, it basically indicates both are similar word. Okay, let's say that I have one more word like angry. Now in this case, with the help of word embeddings, if I'm trying to convert this into vectors, the tentative thing is that obviously happy is the opposite to angry. So angry will be somewhere here. If I probably try to plot this particular vectors over here. Why? Why it is coming so far? Because it is an opposite word. So the distance between this word will be quite high. Whereas the distance between this particular word will be quite less. So this indicates that both the words are similar, whereas both words are opposite to each other, right? And this is all possible because of efficient conversion of the word into vectors, right? And how we are doing this? Again, with the help of word embeddings. But the techniques we have learned till now, it is something like one-hot encoded we have learned, about bag of words we have learned, TF-IDF we have learned. And all these techniques are a part of word embeddings. So if I properly, clearly show you the division, in the first step, if I have the word embedding techniques, so let me just again go ahead and write it. Word embedding techniques are specifically of two types. So this is my first type and this is my second type. The first type is based on count or frequency. Count or frequency. And the second type is based on deep learning trained models. Please hear to this very properly, because this deep learning trained models will give you very good accuracies. Okay. Now in count or frequency, we have learned about three different types. One is one-hot encoded. Second one is something called as bag of words. And the third one is something called as TF-IDF, right? So all these techniques we have learned, right? And we know the advantages and disadvantages. But here we are focusing more on count or frequency, right? But the major one, which is having a better accuracy, which is actually, and all these techniques at the end of the day is also converting words into vectors, or it is converting sentence into vectors, right? Sentence into vectors. But we have seen a lot of advantages and disadvantages. Maximum number of disadvantages are there with respect to all these techniques. And this all disadvantages are getting solved by this deep learning trained model. And the trained model is nothing but, which is basically called as word-to-vec. It's not like we cannot create it from scratch. We can definitely create it from scratch. But again, you require a huge amount of data. And what we are going to do in that, first of all, we are going to understand in the upcoming videos what is exactly word-to-vec and how it is basically converting a word into vectors and how it is solving all the disadvantaged things that were there in this particular technique. Everything we are going to discuss. But just understand that what is word-to-vec? It is a word embedding technique which will efficiently convert a word into a vectors, which will be making sure that both this property, it is expected to have similar in meaning whenever it is converting into a vector space. Along with that, it will also give you a very good representation of the words, right? Sparsity will not be there and all. There are many points which I'm going to discuss in the upcoming videos with respect to word-to-vec. Now, word-to-vec are of two types. One is because the entire deep learning architecture is built on two different types. One is we basically say CBOW. CBOW is nothing but continuous bag of words. Super important. Continuous bag of words. And we are also going to see that how the models get trained. But for this, you really need to have a prerequisite knowledge of how an ANN works. What is loss function? What is optimizers and all, right? The second technique is something called as skipgram. Skipgram. Again, this is a different technique. And again, it is a part of word-to-vec itself. It is a different type of word-to-vec. At the end of the day, we can either use CBOW or skipgram to get an efficient conversion of word to vectors, right? And this is what we are going to see. We are also going to see some pre-trained models of word-to-vec, probably created by Google, and it is somewhere around 1.5 GB big model size. We'll try to download it. We'll try to see, we'll try to execute it. But in the upcoming videos, what we are going to see is that how word-to-vec word embedding works, right? And how it is making sure that all these disadvantages that are present in these techniques is getting removed, right? So this is what we are going to discuss, but I hope you got an idea. At the end of the day, whatever techniques we have discussed till now in converting word into vectors, it falls under word embeddings, right? Hello guys, so we are going to continue a discussion with respect to natural language processing. In this video, we are going to cover word-to-vec. We have already seen what exactly word-to-vec is. It is a deep learning trained model. And again, it is a kind of a word embedding techniques wherein the focus is to convert word into vectors, making sure that the meaning of different words are actually maintained. Like if there are similar words, we'll be getting vectors that are very near to each other if it probably find out the difference. And we'll also be able to see that which all words are completely opposite based on these vectors. Okay. So let's discuss about word-to-vec, and I will give you an idea about like what exactly is word-to-vec and how the words is getting converted into a vectors. In the upcoming videos, I will try to show you that how word-to-vec models are basically prepared with respect to architecture in the case of deep learning models. And for that, you really need to have knowledge about ANN models, right? If you really need to understand that how we can train word-to-vec from scratch, okay? And yeah, let's go ahead and with the definition, and let's see that what all problems it actually fixes. So over here, word-to-vec is a technique for natural language processing published in 2013, and it was published by Google, an amazing company. Already you know that, and they have done some tons of work with respect to NLP. They're doing a lot of research. The word-to-vec algorithm uses a neural network model. We'll be discussing about this, how we'll be using it, how it uses a neural network to learn word association. Please make sure that you understand these words. To learn word association from a large corpus of text. Once trained, such a model can detect synonym words or suggest additional words for partial sentence. So it will be able to detect synonyms, it will be able to detect opposite words and many more things. As the name implies, word-to-vec represents each distinct word with a particular list of number called as vectors. So at the end of the day, we are converting a word into vectors, but this vector will have many things. It will be able to detect synonym words, or it will also be able to suggest additional words for partial sentence. Okay. Now let's understand what exactly this is. Now see guys, in bag of words, TF, IDF, we have already seen, right? Based on the vocabulary size, we'll either get ones or zeros. And in short, we are getting a sparse matrix. In TF, IDF also, we may get decimals like 0.25, 0.6. Then again, zeros are there. In word to vec, it will be a little bit different. Now let me talk about how it will be different. Let's consider that I have a vocabulary, okay? And I have a vocabulary. Let's say I have my vocabulary. So these are basically this many number of unique words I have in my corpus. Okay. Unique words I have in my corpus. Corpus basically means paragraph. Okay. Now let's say the vocabulary words that I specifically have, like something like boy, girl. Okay. And then we have something like king, queen. And if I probably talk about some more words like apple and mango. Let's say in my vocabulary, I have this many words. Okay. Now one very important word I'm going to put up over here, which is called as feature representation. Feature representation. Please listen to me very, very carefully. A very important topic. Now each and every word that are present in the vocabulary will be converted into a feature representation. Now what this exactly means? This basically means that we are going to convert this all words into a vectors based on some features. Now what all features can it be, right? Let me give you a very good example about it, but understand that when we are training a very big word to vec model, at that time you will not be getting a clear idea about all the features. But here, just to make this intuition, to make you understand the intuition, let's discuss about this feature representation. So in the left hand side, what will happen is that, let's say that I will be having a lot of features like this. So I may be having a feature called as gender. I may be having a feature called as royal. I may be having a feature called as age. I may be having a feature called as food. Like this, I will be having a lot of features, and let's say that the total number of features, are basically 300 dimension. That basically means I will be having one more nth feature over here, and the size of this entire features, like if I probably count all of this, this will be 300 dimensions. Let's consider 300 dimension basically means I will be having this 300 features. Now with respect to all this vocabulary, we are going to represent this word in the form of vector considering this feature representation. So this is my entire feature. Okay. What I'm actually going to do, I'm going to take up all these words that are present in the vocabulary. Based on this particular features, we are going to assign one numerical value. Okay. And understand one thing, this numerical value will be assigned based on the relation of these two words. That is the vocabulary and this feature representation that we have. Here I have given you as an example, but when we are training a very large word to vec model, we will not be able to see these features entirely, right? If I take an example of Google, they have come up with this amazing word to vec model, which is basically trained in 3 billion words, I guess, 3 billion words, which is coming from the news feed, right? And that practical example also will try to show you. And at the end of the day, you'll be able to see that each and every word is basically represented by 300 dimension of feature representation. That basically means every word will be having a 300 dimension vectors. Okay. Now this is super important. What kind of values that I can have over here, right? What kind of values I can have over here. Now let's say with respect to boy, which is present in the vocabulary. Okay. And its relationship with respect to gender, let's say that I'm having -1 over here. Let's just consider, okay, -1 over here. Now with respect to girl and gender, the value can be +1 because it is the opposite of boy, right? Opposite with respect to gender, if I say boy is there, opposite of boy is nothing but girl. So -1 and 1, this kind of vectors can come. Now here you can see with respect to the next word. Over here we have boy, we have royal. We obviously know, we cannot say, right? We don't have a sentence that, oh, he's a royal boy. He can be a royal prince or he can be a royal king, right? So there is no proper relationship. So in this particular case, there will be a value like 0.01. I'm just giving you as an example, right? Similarly, we will also be having with respect to boy and age. Let's say that there is not much relation. So I'm just going to put it as 0.03. Okay, very near to 0. Now similarly, I can have all these values over here, and these all values comes through proper trained models like word to vec, which is trained by deep learning techniques like ANN. Okay, and I'll show you in the next video how those models are basically trained. But just understand, over here, each and every vocabulary that we are seeing is represented based on this feature representation. So that basically means for boy, I will be having this vector. So for boy, you can see over here, I will be having this specific vector. Okay, so this all vectors will be here. Okay, now similarly with respect to girl, now you can see with respect to gender, if boy is having -1, then this will be +1, right? Because it is completely opposite. With respect to royal, again, no relationship. So it will be 0.02. Let's say here I'm going to put 0.02 because age with respect to this also no specific relationship, right? So similarly, I will be having other values like this. Now see, with respect to king, I may have gender like there is a relationship with respect to gender and king. So -0.92 will be there. With respect to queen, it can be plus 0.93, So here you can see opposite, right? Opposite over here, right? And similarly, I can have other vectors like over here, royal and king are related, right? So I can have 0.95, okay? And over here, you can see also royal and queen can also be a royal, right? So over here, probably the value can be 0.96, 0.97, very much nearby each other, right? Now understand, because of these vectors, similar words will be very, very close to each other, because if I try to subtract it, I'll just give you an idea about it. So right now with respect to age also, obviously there will be some relationship between age and king, because we say that old king, right, with respect to age. So suppose let's say here I'm having 0.75, here I'm having 0.68. And like this, I will be having multiple vectors like this, right? And we can clearly see, right, over here it is. Now you see, with respect to apple, obviously it will have no relationship with respect to gender. So I can probably write 0.5 or 0.01, something, right? With respect to mango also, it cannot be. So I'll write just 0.23. I'm just saying that, okay, we basically can have some values over here. If it is not having a relation, it will be very much near to 0, like 0.05. Okay, I'm just putting some values. But once we train all these models, right, we will be getting this value. Here I'm giving you a crux idea about like how each and every vectors may look like. Okay, now over here with respect to apple and royal also, I'll not be having much relationship. So let's say I'm putting -0.202, this will be plus 0.02. With respect to age and apple, this may have a very good relationship, right? Because let's say if the apple is kept for 10 days outside, it may rotten up, right? It may not have that nutritional value. So this, with respect to age, it may have a direct relationship. Mango also it may have a direct relationship. So we are going to have this vectors pretty much similar. With respect to food, yes, apple belongs to a food item, right? So this will probably have a good value. It may be 0.91. This is also 0.92. Right? And similarly, I'll be having different vectors, right? So here, what we have done is that each and every vocabulary word is represented based on this feature representation, right? And here, the feature representation need not only be 300 dimensions. It can be 100 dimensions. It can be different dimensions, right? But here, I'm just showing an example with respect to Google. And what will be these features? That will also not be exactly known. But just consider that I'm just giving an intuitive example that yes, based on some relationship with respect to the word, you're able to get this specific vectors. Now there are a lot of advantages with respect to this, why I'm saying you, because suppose let's say if I do a calculation which is like king minus man plus queen. If I do this calculation, and this is a famous calculation which is also written in Google research paper. If I probably do this calculation, the output that I'm going to get is something called as human. Okay. I will definitely get it as human. Why? Over here, human is not there. It's okay. So let me just remove it. Suppose if I say king minus boy plus queen, then the output that I'm going to get, see, king is this vector, right? I'm subtracting with boy and then I'm adding it up queen. At the end of the day, you'll be seeing that the girl will be much more related to boy. So I'm going to get the output as girl. Here I'm just doing the vector calculation, and this is what kind of relations we'll be able to get it. This is an amazing thing. We are getting this kind of relation just by seeing these vectors, which has been provided by word2vec. Again, I'm not going to do the calculation here. I've just randomly stuffed some values. But in the real word2vec use case, you'll be seeing that if you do this kind of calculation, you're going to get girl. And this I will show you practically also as we go ahead. Once we use this Google word2vec, which is basically trained on 3 billion words, which is quite amazing, right? So let me give you another example. Let's say here what I'm doing, instead of using 300 dimension, I'll represent every word by 2 dimension. Let's say I have 0.95, 0.96. Man is represented by something like 0.95, 0.98. Let's represent like this. Okay, I'm just giving some values, okay, some meaningful values, so that you'll get an idea about it. Let's say queen is given as 0.96. Let's say, because this is the opposite of this, right? And again, this can be the similar keyword, similar vocabulary. And with respect to women, let's say that I'm having something like 0.94 or 0.196, let's say. Then what I do is that if we do the calculation of king minus man plus queen, I'm going to get the woman, right, as the output. Now what these vectors represent, that also you really need to understand. It is super important, and that is where I'm going to discuss about something called as cosine similarity. Okay, cosine similarity, super important topic with respect to understanding these things, because if you understand these things and all. Now see, over here king is given by two vectors, right? 0.95, 0.96. So obviously I can basically construct this into a 2 dimension. Let's say that I'm getting king over here, okay, and in order to make you understand, let's say queen is over here, okay, or queen can come over anywhere. Let's say man is over here, right? Man is over here. If I probably say king with respect to gender, right, this 2 is going to be the most nearest word when compared to queen, right? So how do I calculate the distance between this vector and this vector, which is provided in this form? All I do is that I try to probably calculate the distance like this. Okay, I try to find out the angle, and for this, to find out the distance between 2 vectors, we use a distance formula which says it is nothing but 1 minus cosine similarity. Now what is cosine similarity? This is super important to understand. Cosine similarity, I can basically say that cosine similarity is nothing but the angle between these 2 vectors. Let's say the angle between these 2 vectors, let's say I'm just taking as an example, is 45 degree. Let's consider. Then this is nothing but cos 45. Cos 45 is nothing but 1 by root 2, and probably I think this is approximately equal to 0.7071. I've done the calculation. If it is wrong, just let me know. Okay, but over here then the distance between these 2 vectors will be nothing but 1 minus 0.7071. Now if I'm calculating the distance, it is 0.29, let's say. So if I'm getting this 0.29 distance, right, I will say that, okay, almost this particular word are similar. Let's say if I have 2 more vectors, if I have 2 different vectors, one of the vector is basically over here, one of the vector is over here, then the angle between these 2 is nothing but 90 degree. In the case of 19 degree, my distance will be nothing but 1 minus cos theta. Cos theta is nothing but cos 90. Cos 90 is nothing but 0. 1 minus 0 is 1. So I can definitely say this vector and this vector are completely different, because the distance between them is 1. If the distance is nearer to 0, I will say that they are almost similar vectors. Now in this case it is 0.29. I can say that, okay, somewhat similar, right? Let's say if I have one more vector which is in this point only, then I can say that these 2 vectors are almost same, because the angle between them is cos 0. Cos 0 is nothing but 1 minus 1, which is nothing but 0, right? Because over here the angle between these 2 points is nothing but 0, right? There is no angle at all, right? So if there is no angle, then I will be able to find out the distance. In this case, my distance will be nothing but 1 minus cos 0. 1 minus cos 0 is nothing but 1 minus 1, which is nothing but 0. Now, if the distance is coming as 0, that basically means these 2 are same word, right? Now, so this is super important, because recommendation also happens in this way itself. Now, in recommendation, let's say I have a movie which is like I have Avengers. Let's say Avengers is over here. Where do you think Iron Man will come? Iron Man will come again near this or near this at this particular point only, right? Iron Man will be coming, and it will be based on different feature representation, right? Whether it is a comic movie, whether it is an action movie. So action, comic, right? Or comedy, these all are feature representation. Try to understand this. And movie name is basically my vector, my vocabulary. It can be Avengers, it can be this one, right? So I hope you're getting an idea about how word2vec is basically working. At the end of the day, we are basically creating a feature representation of every word. Okay, and we are able to find it out. So yes, this was about word2vec. Now what we are going to do is that you need to understand that how this feature representation is created and how this vectors is basically created. How this vectors, because here I have randomly written boy to gender is -1, boy to girl, girl to gender is +1, because I said that, okay, this may be the opposite one. Now you'll get an idea that how in an deep learning neural network, basically a simple neural network, how this entire word-to-vec is trained. And that is what I'm going to discuss in my next video. Then I'm going to also show you the practical implementation. So I hope you're able to understand this with respect to this, a very good, amazing model developed by Google, a very good architecture with respect to this, and we'll try to solve that in the upcoming video. Hello guys, so we are going to continue the discussion with respect to word-to-vec. Already we know word-to-vec are basically of two types. One is CBOW, which we have already seen previously, continuous bag of words, and scriptgram. In this video, what we are going to do is that we are going to understand that how word-to-vec model is basically created. What is the deep learning model that we are specifically saying, how the inputs and outputs are there and how the model is basically trained. One important thing is that you really need to have a prerequisite knowledge about ANN, loss function, and optimizers. So if you do not have this, I would suggest, first of all, please make sure that you have some knowledge about this, right, before you understand this. Now, with respect to word-to-vec, one more important thing is that in word-to-vec, we also have a pre-trained models, right? Now, if I talk about a pre-trained model like Google, right? Google has a pre-trained model with respect to word-to-vec, which is trained on 3 billion words. And we can also train a model from scratch. Okay. And again, the reason why I'm taking this, because you really need to understand that how that feature representation is basically getting created. Okay. Now let me go ahead and let me say is that, let me take a simple corpus, and let's say that first of all, we'll start with CBOW. Okay. So we are going to discuss about CBOW, which is nothing but continuous bag of words, and how this model is basically created. It is a type of word-to-vec, right? Continuous bag of words. Now, to solve any problem, I will definitely have a data set. So let's say that this is my corpus. And remember, corpus, because all these models, like word-to-vec is trained on a huge data set. Like this particular pre-trained model from Google is basically trained on 3 billion words. So let's say I have a corpus or a statement or a data set or a paragraph. It can be anything. And for just making you understand, I'm just going to take a simple paragraph. I'm going to say that, okay, iNeuron is iNeuron company, or iNeuron company is related to data science. Let's say I have this particular corpus. Now, remember, like this, in a use case, you'll be having a bigger corpus. It can have millions of words, right? But let's say that I'm taking just a simple corpus over here, just a single liner. Now you're going to understand that how a CBOW word-to-vec is basically created and how a model is basically trained with the help of deep learning. Now, first thing is that whenever we have a corpus, we really need to know what is our input data and what is our output data, because word-to-vec altogether is a supervised machine learning, right? So first of all, what we do is that we select a window size. And I'll talk about this window size and why it is super important. Let's say that I'm going to select a window size of 5. Now this window size is super important to basically create your input data and output data. Okay, super important. Like what should be your input data and what should be your output data, so that you can train your model, right? Now this window size 5 indicates that how many words I need to select initially. So let's say I am selecting 5 words. So here is my 5 words. Now from this particular 5 words, I will take the center word. Now understand how I will take up this window size 5 words and convert into input and output data. So let's say this is my input data and this is my output data. Okay. Now the central element that I've actually taken over here is right. Now in the input, I will be having iNeuron company, and then on the right hand side I have related and I have 2. Okay. Now why you may be thinking that I'm taking the forward and the backward, because understand, if I'm taking this as a central word and this will basically be my output word, okay, is. Okay, this is basically my output word. Now it should be knowing that what all words are in the forward context and what all words are in the backward context. So that is the reason we are creating in this particular way, so that this is output should be knowing about its forward word and its backward word, just to get some idea about the context of that specific sentence. Now this is the first step. Now when I took the window size as 5, the initial 5 words, I divided my data set into input and output. Perfect. Now the next step is that I will go ahead and I'll move this window by 1 step and take the next 5 words. So the next 5 words over here is nothing but, so here this is my sentence 1, input 1, and now this will become my input 2, and here I will be having company. Okay. And again, from all these 5 words, which is my center word, so this is basically my center word, related, right? So related. So here I'll write company is 2 and data. So this is my second input, and over here the output will basically be related, right? Then similarly, I will go to the next step and I will push this windows to 1 step more. Okay. So here now I'll be having my third sentence with respect to my input and output. And the third sentence again, which is the central word. So this will basically be my central word. So here you have 2. Okay. And here I'm going to have is related. Okay. And then the right hand side, data and science. Now you may be thinking, Krish, should we only take the window size as 5? No, you can take any value. You can take any value. And why this window size is playing an important role, I'll just say in some time. You can take up any value, but don't take an even number. Take an odd number so that I will be getting the central element which I'm taking as an output will have the correct number of words in the forward context and in the backward context. Okay. So is related data science is there, right? Now, which is the central word over here? 2, right? So I'm just going to write it as 2. Now this became my input and output. Now what I'm actually going to do is that I'm going to train my model with this. Very simple, right? I'm going to train my model with this. Now how the training will basically happen. Now one very important thing that you need to understand. Over here you'll be seeing iNeuron company related to all these inputs and outputs. So I cannot probably send this text directly. I need to convert this into some vectors initially to send it in as an input to the neural network also. So for this, what I'm actually going to do, first of all, you know that how many number of words I have, how many number of words I have in the vocabulary. I have iNeuron, I have company, I have is related to data science, right? So they are around 1, 2, 3, 4, 5, 6, 7, right? 7 words are there. Now, if I probably use one hot encoding technique, now see this. Okay, this is super important. In one hot encoding technique, if I probably consider iNeuron, let's consider the first sentence. Over here, I have iNeuron, and then I have company, then I have related, and then I have 2, right? So for all these words, how I'll be giving the one hot encoding representation, wherever there will be iNeuron, I'm just going to make it as 1. Remaining all will be zeros. So there will be around 1, 2, 3, 4, 5, 6 zeros. Similarly, when company is there, I'll make this as 1 and remaining all will be zeros, right? Similarly, related is in the 4th word. So I'm going to make it as 0, 0, 1, 0, 0, 0, and then 2 is present after this. So I'm basically going to write it as 0, 1, 0, 0, right? So this is pretty much clear till here, right? So here you can see that I've basically done this, a simple one hot encoded format. That basically means if I really want to pass iNeuron, I need to give this as my vector. This is what is the understanding. And this vector is basically given by 7 dimensions. So 7 vectors I'm giving it over here, right? 1, 0, 0, 0, 0. If I'm sending company as my next word, then this should be the vector it should go, right? Then if I'm sending related, this should be the vector I should go. So similarly, all these particular words will be converted into this particular vector using one hot encoding. Now let's go to the next step, which is super important. Okay, super important. What does CBOW basically mean? Continuous bag of words. Okay. This is nothing but this is a fully connected neural network. Now you will be able to understand how these models are created. Fully connected neural network. Okay. Now in this fully connected neural network, you will be able to see one very important thing. One is, first of all, just understand how many number of input should I be giving, right? Like how many words I will be giving as my input, right? Since my window size is same, Window size is 5. All my inputs are fixed. I hope that is very much clear, right? Now in this particular problem statement, you'll be seeing I'm giving 4 words in every sentence. So my input is basically fixed. Now, iNeuron, when I give my word iNeuron, let's say in the first case, I give my sentence 1, and this is my sentence 1. When I give iNeuron is represented by 7 vectors over here. It is represented by this vector. Then company is basically represented by this vector. So if I probably see in fully connected layer, my first input layer will basically be nothing but, so here you'll be able to see, this will be my input. Okay. And this is super important, guys. See this. So this will be my input, my first input word. Okay. And understand I'm creating this circle as my inputs. Okay, I'm just creating this circle as my input. So if you see 1, 2, 3, 4, 5, 6, 7. 7 inputs I'm giving it, right? Now when I give this 7 inputs, then similarly how many words will be going? 4 words will be going, right? So 1 word, 2 word. So this is basically my input layer. So this layer is nothing but my input layer in a fully connected layer. A simple ANN, if I probably consider an example of ANN. So here also how many inputs I'll be having? 1, 2, 3, 4, 5, 6, 7, right? And this is my first word, second word, third word, fourth word. So I will be having 4 different words over here that will be going. And each word will be having a dimension of 7 vectors. 1, 2, 3, 4, 5, 6, 7, right? I'm not giving this value. Don't consider that these all are zeros. Okay. I'm just saying that these are my input layer, input circles. Okay. That is how we create it in ANN, right? And then probably I have my last one. So this is my input, right? I'm basically designing the neural network, how it will look like when we are training a word to vec. So these are my four words. Understand, in the first case, I'm going to pass iNeuron over here. So let's say I'm going to pass over here iNeuron. This will be my input over here. This is represented, iNeuron will be represented by 1, 0, 0, 0, 0, 0, right? And similarly, if I go to the second word, that is like company, then it will be represented by another word like this, right? It will be represented by a different vector like 0, 1, 0, 0, 0, 0, 0, right? 7, it will be 1, 2, 3, 4, 5, 6, 7, right? Now, similarly, other words will be represented like this, okay? So this becomes my input layer, okay? And every input is basically given by a vector of 7 dimensions. So because I'm representing every word based on the vocabulary size using one hot encoded. Now this becomes my input layer. Now let's go to the middle layer, that is called as a hidden layer. Now in this hidden layer, this is super important. Just pause the video and guess what will be the size. You know our window size is how much? Our window size is basically 5, right? So I'm just going to make this as my window size. Okay. So this is my window size. Now in my window size, if you remember, how many we are having in our window size? Our window size is nothing but 5. So I'll be having 1, 2, 3, 4, 5, right? Window size is basically 5. So in my hidden layer, I'll be having this 5 vectors. Okay. So just understand that with respect to this 5, our window size will be set over here. Okay. Now with respect to the output, in output, how many values I have? I just have one value, and each word, I just have one word in the output, right? And each word is represented by a vector of 7. Because if I am also considering this is using one hot encoded, I'm going to get this vectors of this dimension, that is 7, right? So what I will be doing in output, I will basically be having another output layer like this, which will again be having 7 different outputs. 1, 2, 3, 4, 5, 6, 7. Okay. Now this is how my fully connected neural network will look like. Now you need to understand one thing. Over here, each and every node will be connected to the other node, right? Like this. Like this, it will be connected. Like how an ANN will work. It will be connected like this only, right? Similarly, right? Now, similarly, these all will be connected to this also. So in short, I can basically make a very simple connection like this, which will look like this itself. And this will be entirely connected to this, right? Understand, all these lines will have some initialized weights, and we need to train these weights. And this is what it happens in ANN, right? Similarly, this will be connected to this. This will be connected to this. This will be connected to this, right? And finally, this will also be connected to this, right? So everything is basically getting connected. And from the hidden layer, this is my hidden layer 1, HL1, and this is my output layer, right? Now from this hidden layer, it will basically get connected over here, and this will get connected over here. Okay. Now understand one very, very important thing. Okay. This is super, super important. Fine. We are connecting it with the help of loss function. We'll also do forward and backward propagation. Now let's say we'll consider, let's pass this particular word, iNeuron company related to. So I have passed iNeuron company, and here also you'll be able to see I'm passing related to. Very simple. Okay. Let me just zoom out a bit. Okay. Now once I pass all these things, what happens over here? With respect to this 7 output, I already know what is my real output is, right? I'll be getting some values over here. Okay. I'll be getting some values. Okay. But the real output is what? If I consider is my third word. So is my real output. So this will basically be represented in this vector format, that is 0, 0, 1, 0, 0, 0, 0, right? But after training, while we are training the model with different weights, this is my true output. This is my Y. I may also get different Y hat, right? I may get some values like 0.25, I may get some values like 0.33, then like this 0, 1, 0, 0, 0, something like this. Then what we do, we basically calculate the loss function, and based on this loss, we need to reduce this. We do the backward propagation, right? Backward propagation. And we do it unless and until the difference between Y and Y hat are minimal. Okay. And this process is continuous. Very simple. But now you really need to understand one very important thing. Very, very important thing. Now, since this is giving me a specific output, okay, this is basically giving me a specific output. When I say my middle layer is basically window size of 5, that basically means over here in the word to vec, when I said I will be getting a 300 dimensions over here, when I'm using Google word to vec, this is all because of this window size. Okay. That basically means if my window size is 5, I'm going to get the output as 5 for every word. That basically means when a word is getting converted into a vector, I am going to get a size of 5 vectors. And this will basically be my final output. Now, I hope you are able to understand. Again, let me repeat it. The reason I have actually selected window size is equal to 5 because I want to probably provide a feature representation with a vector size of 5. Okay, that basically means every word will be converted into a 5 vector. Now, when I took an example of Google, which was getting converted into 300 dimension, that basically means my window size is 300. And more the bigger window size, the better the model can basically perform. Okay. So in this case, you'll be able to see that over here, my window size is 5. That basically means if I see from starting, right, my metrics for every word will be 7 cross 5. That many number of weights will be there. Then here also I'll be having 7 cross 5 weights. Here also I'll be having 7 cross 5 weights because I'm giving 7 different vectors. Here also I'm having 7 cross 5. But in this case, I will basically be having 5 cross 7. Now, what does 5 cross 7 basically mean? When this loss gets reduced, then my final vector will look something like this. This all will get connected to this. This all will get connected to this. Let's say it is getting connected to this one. It is getting connected to this one. It is getting connected to this one. So once we have this particular connection, let's say our first word over here is, what is our first word? If you probably see, what is our first word with respect to this particular vectors with vocabulary? You'll be seeing iNeuron, right? This is my vocabulary. The first word that is basically getting represented over here is iNeuron, right? So iNeuron will have an output dimension of 5 vectors because I'm getting this 5 vectors over here joined to this. So this 5 vectors will be like 0.92, it can be 0.94. Based on the training, it can be 0.25, it can be 0.36, and it can be 0.45. And this is based on some feature representation. So I hope you are able to understand. And this is how iNeuron will be represented. The second word that we have in the vocabulary, that is company, right? This will again get connected to this company, This will also get connected. This will also get connected. This will also get connected. This will also get, and this entire word will be the vector for the company itself. And for the company, we may have a different vector, but again, the size will be 5 dimension because our window size is 5. And this training of forward and the backward propagation, when the loss is minimal, then only we'll be able to get the vectors. And that vector is basically taken and it will be represented in the format of the feature representation for each and every word. So guys, so we are going to continue the discussion with respect to natural language processing. In this video, we are going to discuss about the second architecture, that is skipgram. Now, already I've actually shown you how does CBOW actually works, continuous bag of words. And I've also showed you that how the neural network gets trained, right? Now, what is the difference between CBOW and skipgram? What is the difference between the architecture? It is very simple, guys. Right now, just focus. I'm going to take the same data set over here. Let's say that iNeuron company is related to data science. I've written over here, right? And with respect to this, you can see that I've created my input and output. Now, if I am using skipgram, then the thing that is going to change is that everything will be same. Let's say that I have taken the window size as this. So if I probably go ahead and show you, now what will happen is that before the input was this specific test and the output was this specific test. Now with the help of skipgram over here, initially, let's say that if this was input, now this is going to become the input and this will basically be the output, right? And this is with respect to window size is equal to 5, right? Window size is equal to 5. All the steps will be same. Only what we are doing is that we are changing the input and we are changing the output. Before, the input was this all text and the output was this. Now what will happen is that entirely when we are creating this neural network, now in the input, let's say that I have this is word, related word, to word, right? So in the input, I'm going to basically have input layer with 7 vectors that will be going. Why 7? Because if we probably see this, our vectors, how many number of vocabulary, what is the vocabulary size? 1, 2, 3, 4, 5, 6, 7, right? So initially in the input layer, I will be giving input, which will be basically having 7 vectors, 7 dimension vectors. And then in the middle, I will basically be having my window size vectors. So window size is nothing but 5. 1, 2, 3, 4, 5. Just understand this. These are just nodes. Okay. And in the output, you can see that I'm having 4 words, right? So everything that is present with respect to this, right? Similarly, this will get constructed over here at this point of time. So over here in the output layer, you'll be able to see that I will be having 1 word, 2 word, 3 word, and the 4th word. So this is what is the kind of output we will be getting. And again, here it is very much simple because every one will be like 7 dimension over here again, right? So I hope you are able to understand. We have just changed the direction with respect to this, right? So this will be my input layer. So here you can see that we will basically be having a 7x5 matrix with respect to the weights, because weights initially be randomly and initialized, right? And then we need to train this, right? And then we will be having with respect to this all, I'll be connecting here to here, here to here, and this will basically be a 5x7 matrix with respect to weights, and then this will be 5x7. Similarly over here you'll be seeing that this will be 5x7, and below one will also be a 5x7. But in with respect to that, you can see that initially when I give the input is will be the is vectors will be going over here. And as you know that is the third word, so this will be going like this, right? So 0, 0, 1, 0, 0, 0, 0. So this is the vectors that will be going over here. And again, since my window size is 5, over here you'll be able to see other vectors that will get initialized. Randomly, this all will be connected with weights. So 7x5 weight matrix will be created. And with respect to this, our forward propagation will happen. And obviously, you know that if you probably know ANN, right, what all things happens in between the hidden layer. The input weights is getting multiplied by the weights itself, and then a bias is added and an activation function is applied on top of it. In the output layer, we basically apply a softmax function. Softmax function, so that we compute it with y and y hat. Y hat is the predicted one, y is the real data. In this particular case, this is my y. Sorry, this is my y. Right, in the first case, y is I neuron. So I neuron, whatever things will be there, whatever vectors will be there, here you will be initializing it. Right, so here I basically apply a softmax function. Let's say with respect to I neuron, my y is nothing but 1 0 0 0 0 0 0 0, 7 zeros, and then y hat will be computed since we apply a softmax over here. Right, so y hat will be something, right, some values over here, and then what we do, we calculate our loss function, and we make sure that we keep on doing the forward and the backward propagation unless and until all the loss function decreases. Right, the loss value decreases, and finally you'll be seeing that whatever is connected, right, this particular word will be shown in the form of 5 vectors. This word will be shown in the form of 5 vectors once the loss is completely minimized. So same process, you should definitely know how the ANN actually works, how the optimizers actually work, and this was just a brief idea about scriptgram. Right, now how can we improve this, or the basic question is that when should we apply CBOW? So the question is, when should we apply CBOW or skipgram, right? The simple thing is that according to the research, right, whenever you have a small data set, small corpus, we can definitely go with something like CBOW, that is continuous bag of word. If you have a huge data set, you should definitely go with skipgram, and that is proven in many research paper. So I'm just giving you the direct observation out of it so that you'll be able to do this. Now let's say if you want to increase CBOW or skipgram, how can you basically do it? One thing is that you should increase your training data set. Increase the training data. That basically means the more the training data, the better the accuracy, right? Increase the training data. The second thing is that you can also increase the window size, which in turn leads to increase of dimensions, increase of vector dimension. This is super important. Okay, so here I'm saying how to improve CBOW or skipgram. So this is what you can basically do. Increase the window size. Okay, this is super important. Increase the window size. I'm again going to take this separately or forget it out. So over here again, let me write this. We have to increase. We can also increase the window size. Instead of having 5, I can make this as 100. You know, so obviously with the increase in the window size, increase the window size. If we are increasing the window size, that basically means the vector dimension is also increasing, right? The vector dimension is also increasing. So when we keep on increasing and try it, you'll be able to see that we'll be getting better performance. So this is also you can basically use. You can increase it. Now when we see in the next example, right, we'll be using a pre-trained model with respect to Google. So Google word2vec, right? Now this is basically trained in 3 billion words. I guess it is 3 billion words, 3 billion words. And it is going to give me a feature representation of 300 vectors, sorry, 300 dimensions. That basically means, suppose if I have a word cricket, okay, since cricket is always there in the news, this 3 billion word is from the Google News, right? And Google is a very big company, guys. With them, this amount of data, it is very much easy. So what they are going to do is that if we give a word called as cricket, then it is going to basically convert this into a 300 dimension vectors. Okay, vectors. This is super important. 300 dimension vectors. Okay. So I'm just going to write it as 300 dimension vectors. And this all example I will try to show you when we use this. What we'll do is that in the upcoming session, we'll try to use a pre-trained model also, and we'll try to also make sure that we train a new data set from scratch with the help of word2vec. And that we are going to basically do with the GenSim library. Okay. So yes, this we will be doing in the next video. So I hope you have understood both the architecture. One is CBOW and one is the skipgram. Hello guys, so we are going to continue a discussion with respect to NLP, and in this video we are going to discuss about average word to vec, a super important topic again, because just with the help of word to vec you'll not be able to solve the classification problem. You really need to perform something called as average word to vec. Let's take a simple example and I'll try to show you. Right now we'll just discuss with respect to theoretical intuition, but as we go ahead we'll be discussing about practical part also and how we can implement average word to vec also. So over here I have my text data, the foot is good and the output is 1, 0 and 1, and you can see all these are my documents. Now as you know that with the help of word to vec, what we do is that we take every word and we convert that into vectors. Let's say that I'm using a Google pre-trained model. Okay, I'm using a Google pre-trained word to vec model. Pre-trained word to vec model. Now in this Google pre-trained word to vec model, what I'm actually doing is that over here you can definitely see that. Okay, so if this is my sentence, the food is good, right? Now the will get converted into some vectors. Okay, and I've already shown you that with respect to feature representation, we will be getting a vector of 300 dimensions. So let's say this is the vector of 300 dimensions. Okay, so the will get converted into 300 dimensions with respect to this. Okay, the will be there. Now coming to the next word, that is food, right? Food will also get converted into 300 dimensions. And that is what happens with respect to this word to vec, right? Every word that is present over here, like is, will also get formed in 300 dimensions, and here also all these words will get converted into vectors with respect to this many number of dimension. Okay, perfect. So till here I think you're superbly clear, because we have already discussed about all these things in our previous session. But now you need to understand one thing, is that when we have this kind of sentences, and if we are basically writing this many number of dimensions, basically this many number of vectors are there. Let's say this is my 300 dimension vector, which is basically getting converted for the food and this. In the real world scenario, I should be converting this entire sentence into vectors, right? But here you can see I'm getting vectors for the also 300 vectors. For food I'm getting separately 300 vectors. For is I'm getting 300 vectors, and for good I'm getting 300 vectors, right? 300 dimension vectors. Now this is a problem. At the end of the day, for this entire sentence, let's say if I'm getting a 300 dimension for this entire sentence, let's say this is my sentence 1 or document 1. My main aim should be that I should be getting only one 300 dimension with respect to this, so that I can take this as an input and this will basically be my output, and I can basically train my model. Right, but here you can see that since we are applying word to vec, every word is basically getting converted into a separate 300 dimension vectors. So in order to solve this, what we do is that we take all these vectors, and we find the average of it. Once we find the average of it, then we try to write that particular vector over here for this entire sentence, and then this vector will be considered for this entire document or sentence. Similarly, the second vector also is there. We will go ahead and calculate the average of it and we'll write it over here. Similarly, like this, every vector will basically happen, right? For every vector, so all the word vectors, you know, averaging is basically happening, and that is the reason we say average word to vec. Okay, and why this will work? Because see, at the end of the day, you'll be seeing that we just require the vectors for this entire sentence. And right now we have for every word a separate 300 dimension vectors. So if we are trying to take out the average of all this particular vector, and if we try to write down as one vector, and this will also be, the length will obviously be 300 itself, right? This will be 300 dimension itself. But now with respect to this particular vector, I will be having my output. I can pass it through my model and get trained with respect to this. So at the end of the day, what happens is that if I'm having a sentence like this, after applying average word to vec, I'm just going to get, let's say if I'm using the pre-trained model, I'm going to get a 300 dimension vectors, which will be all this particular average of all these particular vectors itself. and all this will be over here, and I will be getting my output variable, which is already over here. And similarly, this will happen for the second word set document, third document also. So average word to vec basically says that, okay, we are not doing anything. Whatever vectors is getting converted, I'm just trying to average out each and every vector with respect to that, right? So over here, let's say the is having 300 dimension vector, food is having 300 dimension vector, is having 300 dimension, good is having 300. For every line by line, all the vectors, I'm just averaging that out and I'm actually finding out a value. And why we are doing this? Because we really want only one specific set of vectors for the entire sentence, right? So this is what average word to vec is basically. And for any text classification, we basically needed to solve through this specific way only. Now in the upcoming tutorials, what I'm actually going to show is that I'm going to basically use a library which is called as gensim. Okay. And there is also a library separately which is called as glove. But if you probably understand gensim, you'll be able to do everything. So first of all, we will go ahead and we will see with respect to a pre-trained Google word to vec. And then in the second instance, what we are going to do is that we are going to train a word to vec from scratch. That basically means we'll take a data set and we'll try to train a word to vec model. And again, with the help of gensim library, we'll be doing it. So I hope you got an idea about average word to vec. At the end of the day, why we are doing this, because for the entire sentence, we want some vectors. And since we are combining all this particular word, that semantic information will also be maintained, right? So yes, I will see you all in the next video with the practical implementation. Hello guys, so in this video, we are going to basically see the word to vec practical implementation. I really want to show you some Google pre-trained models and basically give you an idea like how word to vec creates a vector, right? So for this tutorial, I'm going to use a library which is called as gensim. So let's go ahead and let's install this particular library. So you just need to write pip install gensim. So here you can see that requirement is already satisfied. And what I am actually going to do is that I'm going to import gensim, and from gensim.model, I'm going to import word to vec and keyed vectors. Okay. And I'll talk about this, why these two libraries are specifically required. Now, one very important thing for this, as I said that to show you the practical implementation of word to vec, here I'm going to take a Google pre-trained model. In the upcoming video, I will try to show you a different model which can be trained from scratch. But here I'm going to show you a Google word to vec pre-trained model and what this particular model is all about. So I'm basically taking a word to vec Google News 300. Okay. And this is basically a pre-trained vector trained on Google News dataset about 100 billion words. The model contains 300 dimensional vectors for 3 million words and phrases, right? These phrases were obtained using a sample data driven approach and distributed representation of this and all the research paper and everything is basically given over here. Okay. So this same model we are going to use, and we are going to see that how it can easily create a vectors whenever we give any kind of words. So in gensim, you have something called as API, right? So there is a library called as API. So you just need to write import gensim.downloader as API, and you just need to write API.load and basically the model name, right? So the model name is nothing but word to vec Google News dash 300. Okay. Now, once you do this, all you have to do is that when you provide any word inside this WV variable, which is nothing but this is an instance of this specific model, it will try to give you the vector. I'm not going to execute this line of code because I've already done it, because the model size is 1662.8 MB, right? So it will probably take some time for you all to download. So I have already downloaded this so that I can record the video directly. You can just go ahead and download it. Now let me go ahead see that how the king vector look like. Okay. So this is basically the king vectors, how the word is basically converted into vectors, and the dimensions that you'll be seeing, right? How many vectors are there? As said, from here, right, we have 300 dimensions. So this is what we are getting. This entire vectors you'll be able to see will be having 300 dimensions. So if I probably use this vector underscore king dot shape, right? So if I execute this here, you will be able to see 300 dimensions, right? So with respect to this, you use any kind of word, you will be able to get some kind of vectors. Now let me give you some of the example. Okay, suppose I make over here, and for this particular vector, what all things I use this WV variable, which is a word to vec object, right? All I have to do, I have to give this and give any word of your choice. Let's say I want to give cricket, right? So if I give probably cricket, you'll be able to see that the vector is automatically generated. So here is again the vector which you are basically getting with respect to this particular shape, that is 300 dimension. Now this WV variable, right, which is a word vector, it also has some of the functions. You can actually use something called as most underscore similar. Now let's say that I've given this most underscore similar. I'm saying that from if I'm giving this cricket word, right, which is the most similar word present in this entire corpus, right, and I'm actually going to use the same word to vec object, and I'm going to find out all the words. So if I execute this, here you'll be able to see the most similar with respect to cricket. You know, it will first of all try to convert into a vector, and then it will probably check whether that vector is being able to see any similar kind of words or not. So these are all the words that is similar to cricket in that specific corpus. So you have cricketing, it is having like 0.83 similarity, 0.83% similarity, then cricketers 81% similarity, then you have test cricket, here you can see 80% similarity, 20 cricket, right, you have 80% similarity, then you have cricket, then you have cricketer, all these things, you know, they are showing some kind of similarities with respect to this Google News feed, right? Now similarly, if I really want to find out which is the most similar word with respect to happy, you'll also be able to see I'll be having words like glad, pleased, ecstatic, overjoyed, thrilled, satisfied, proud, delighted, and understand that these all are similar words when I compare to happy, right? So it is also being able to say that, okay, these are the similar words when compared to the happy word, and they're also being able to show with respect to how much distance. And I've already shown you how this distance is basically calculated, right? So we have a concept of cosine similarity and all. Similarly, I can also provide two words, and I can basically say that, okay, how much this two word are basically similar. So if I probably execute this, here you'll be able to see wv.similarity. I'm getting hockey and sports are somewhere around a 53% similar, right? Now this is very interesting. Okay, I'm going to take the vector of king and I'm going to subtract with the vector of man, and I'm going to add the vector of woman. Now let's see what will be the kind of output vectors that I'll be getting. Okay, so once I do this, in short, what I'm doing, I'm subtracting king minus man plus woman, and obviously the answer should be queen, but I really want to prove you through the vectors itself whether we are able to get the queen or not. So here I'm going to execute this. I got my vector, so this is my entire vector. So this is my entire vector, and again this vector is of 300 dimensions. Okay, so this is my entire vector. Now what I'm going to do, I'm going to use wv dot most underscore similar, and I'm just going to pass this entire vector over here. So once I execute this, here you'll be able to see that, see, king is the first. Obviously king should be the most similar vector, but here I'm getting queen, monarch, princess, crown prince, kings, sultan, queen resort. But here you can see that the most similar word after king is queen. So the kind of vector we are getting after doing all this particular subtraction matches more towards the vector with respect to queen, right? And this is what we are able to get with the help of word to vec. Try to use this, guys. This is an amazing model altogether. You'll be able to see that you can actually use this model itself. You know, you can actually use word to vec Google News 300, which will be able to solve many problem of yours. And this is just a brief idea about a pre-trained model, you know, how a word to vec pre-trained model looks like. You can also take your own text and train it from scratch, but again there is a different process for altogether, and this entire thing I've executed in Google Colab because the model size is quite huge. Okay, so in the upcoming videos, what I'm actually going to do, I'm also going to show you a word to vec technique by using GenSim, where you can train the model from scratch. Okay, so yes, this was it for this particular video. I will see you all in the next video. Thank you.